Yeah, you don't want to be stuck in one place. It's true. Yeah.
I wanted, we have them and they work for these speakers.
Yeah.
But they don't plug into the computer.
Right.
So. It would have been super
If
complicated.
I speak from here, that's not big enough, is it? I have to speak from here.
No.
Well, we've turned all these off now.
This mic is good, but we can turn these back on now, I think. Yeah.
Yeah.
So let me mute us on Zoom.
How's that? Hear me out there? Yep.
Yeah.
Yeah, no feedback. How's that?
Thanks for coming down for the start of day 2. It's a bit of a different format from what we had from yesterday. We just have talks in this morning session until 10:30. When there's a coffee break, there'll be 4 talks. And then at 11, we're going to have our keynote event with Prof. Steve Benner from 11 to 12. And then we'll have a lunch break. And then the afternoon, we're going to have the poster session. So it's a good day for talking and looking at the posters and really catching up with everybody. So it's and we're very honored, of course, to have Steve as our keynote for this conference. So that's tremendous. Should be a great day. So without further ado, we'll get started. Our first speaker is Andy Tomkins from Monash University. He's a prof down there and a meteoriticist and economic geologist and all around good guy. So thanks for coming up. And I'll let you know about.
Thanks. All right, thanks for that, Martin. I'm going to actually talk to everybody about some more samples to pick up while you're on your JAXA mission, actually. So let's see how we go. So what do people normally think of? What do you guys normally think of when you think about when somebody says to you life and meteorites? What do you think about? Do you think about panspermia, the idea that you might have blasted off a bit of the Earth, a chunk of the Earth, and brought life to another planet? You might think of abiogenesis, where meteorites have the right sort of ingredients for life. We're going to talk about a little bit about that sort of stuff, the ingredients in meteorites. But we're also going to talk about this idea that meteorites are potentially places, maybe the best places to look for life on another planet. So let's get into it. To start with, we need to know what's in a meteorite and what are micrometeorites and what are in them. So probably a fair few of you know, but some of you probably don't. Meteorites are full of very reduced minerals. So this particular slice through a meteorite is just showing you lots of iron nickel metal, all these little bright specks, reduced iron. And there's lots of other things in there as well. So there's reduced sulfur. This mouse is fun. There we go. Reduced sulfides in here, metal in there. And importantly for biology, there's lots of reduced phosphide in some meteorites. And so it becomes one of the only places you can get reduced phosphorus on the surface of Mars, for example, because Mars is just covered in basalt. Basalt has lots of apatite in it, which is calcium phosphate, and it doesn't weather very easily. So it tends to not make phosphate available. Whereas meteorites, this stuff is very unstable on the surface and weathers pretty easily. And of course, we heard yesterday about what's in some of the carbonaceous chondrites. They have about 0.4% of all sorts of different organic compounds in them. We heard much more detail about that yesterday. So what are micrometeorites? Micrometeorites are probably best thought of as the tiniest little bits you get left over from big collisions in space. So normal meteorites are fragments of collisions, and micrometeorites are kind of the dust and sand sized bits. And they basically come through the atmosphere. Some of them evaporate entirely when they come through the atmosphere like this. They're just those shooting stars you look up at night and see. A sand grain sized bit will light up for a few seconds and then quench to a glass or interlocking crystals. And you end up with these tiny little spherical particles that are about, probably the most abundant are around about 50 to 100 microns in size. So they're tiny little sand particles, really smaller than most sand particles really is the best way to think of it. So 50 microns is about the width of a human hair. So that gives you a sense of scale. Okay, so this talk's kind of in 2 parts. There's a part about micrometeorites and whether they'd be good places for microbes to get nutrients on Mars. So the idea here is that NASA's been following the water on Mars for a long time. We think that's not such a good idea because there's water all over the place. Maybe you should follow the nutrients. And the nutrients are things like reduced minerals that things like chemolithotropes can use for energy. So the idea for this project sort of stemmed from this sort of observation that Curiosity's been making where we have a bedrock surface there. There's a sand dune up the top that's been blowing across the bedrock, and all the heavy, dense particles are being left in those cracks there. So we thought we would go to an analog site on the Nullarbor and look for what happens to the micrometeorite distribution in different places. So we looked at cracks in bedrock, gravel on bedrock, gravel after wind erosion, and sand dunes as well. So this is just a normal piece of limestone bedrock. We've cleaned out the cracks. That's a piece of limestone pavement with lots of gravel on the surface. This is the stuff that's left behind after winds blowing all the light stuff away. It's all the dense and heavier and bigger particles. And then a normal salt clay pan, all the heavy particles again have been left behind after wind erosion. And that's a sand dune, which is where all the wind-blown particles accumulate. So we just basically collected samples of that stuff and did a whole bunch of processing, and we found well over 1,000 meteorites. They're pretty easy to spot, pretty easy to separate. It's not too much difficulty. There's a table there of all the data. So for 2 different size bins, 125 to 250 microns and 250 to 500 microns. So they're pretty big for micrometeorites. The overall message there is that the residues of wind erosion, like cracks and deflation surfaces, have hundreds of micrometeorites per kilogram. So lots and lots of these things. This is on the Nullarbor, which is a desert. It gets a little bit of rain, but it's got a young surface compared to the surface of Mars. So they're going to be all over the place on Mars is where we're heading towards. We did some modeling of atmospheric entry of micrometeorites, so tiny asteroid particles through the Martian atmosphere. And you'll see at the bottom of all these slides is kind of the takeaway message for all these several slides coming up. And the overall message will be that there should be lots of micrometeorites on Mars. And so let's step through some of these slides here. So most of them are entering at slower speeds than Earth's atmosphere because Mars has lower gravity. The entry temperatures for an given initial size are lower than on Earth because the entry velocity is lower largely. So small micrometeorites experience much less heating than big ones. And below a certain size threshold, this applies on Earth as well as on Mars, below a certain size threshold, they don't melt at all. So in this particular model here, for that particular entry velocity, samples, micrometeorites below 400 microns don't melt. And on Earth, that's more like about 30 microns. So that's much bigger on Mars. And what that means is we can go to Antarctica and pick up micrometeorites there, and some of them will be unmelted carbonaceous meteorites. So really, really organic compound rich material, much richer than in normal meteorites. It's like 50% organic material, some of them, crazy amount of stuff in these things. Basically small particles, in small particles, volatiles survive entry easier. So this is bigger particles on Mars will survive better. So that means organic compounds and minerals that often evaporate in atmosphere will survive better on Mars than on Earth. The things like metal and sulfides and phosphides, reduced phosphorus, will survive entry better on Mars than on Earth. And so it turns out this is the abundance of micrometeorites as a function of size, and basically really, really small ones are much more abundant. And so it turns out that most micrometeorites on Mars are probably unmelted and probably unaffected by the atmosphere as they come through. So there should be lots of cosmic dust on the surface that's barely changed from when it was floating around in space. So what do we see on Mars? It turns out that nobody's really looked, but when we look at other heavy particles, they're obviously concentrated in fractures. So these blueberries are basically iron oxide particles. They're dense compared to other minerals on the surface of Mars, and they've accumulated in bedrock cracks as well. There are tiny little round things that have been found on Mars. These could be iron micrometeorites. They're pretty big for a micrometeorite, but they could also be blueberries. People haven't analyzed them properly. I think at least this one is metal. These are the little round things that these arrows are pointing to in here. Could be micrometeorites, they could be blueberries. People haven't analyzed them, so they don't know. And when you look at just the top of a sand dune, you see lots of these little round particles you can see with the yellow arrows there. Are things that we would pick out as possibly being micrometeorites and test them in the lab back on Earth. So on Earth, the earliest microbes were chemolithotrophs, which gain energy by oxidation and reduced iron and sulfur. Most of the Martian surface is basaltic, so there's only olivine, pyroxene, plagioclase, and a bit of apatite. There's not much that they can use there. So micrometeorites basically supply a lot of nutrients that aren't otherwise available. And they tend to accumulate in particular places on the surface. Reduced phosphorus has been implicated in the emergence of life. So experiments mixing this mineral here, schrebersite, with organic hydroxyls produce the precursors to RNA. So all the ingredients for the emergence of life are found in micrometeorites as well. And so they're expected to be enriched in particular places on the surface of Mars. So that's the micrometeorites one. We know where to look for life on Mars in exploiting micrometeorites potentially. But what about meteorites? This is some work that was done by Alastair Tate, who in his PhD, and then also some postdoc work. And Alastair was supervised by Sasha and myself. So this is Sasha Wilson, who's over in Canada now. And one of the earliest things we thought about was the idea that meteorites on the surface of Mars should be grade standards. And that's because we have over 70,000 meteorites in our global collection now. And there's been thousands and thousands of papers written on what's in meteorites. We know their chemistry really well, very narrowly defined, whereas we don't know the chemistry of the Martian surface very well by comparison. The isotopic variability in meteorites is very small, whereas the isotopic variability on the surface of Mars is quite large. That means if you go and analyze some sulfur in a meteorite and it has a big deviation from its expected value, something else has happened to it. Could be biological, could be some other process. It's a good place to look for isotopic changes. So that applies for sulfur isotopes. It applies for carbon and oxygen isotopes as well. And there's been a fair few meteorites already found on the surface of Mars. Most of them are ions because they're easy to spot. There's probably lots of fragments of meteorites on the surface that are difficult to recognize because they're covered in red dust. But there's lots of it there. And you'd expect that it's an old surface and meteorites should be accumulating there. If I wanted to go looking for meteorites anywhere, Mars would be better than anywhere on Earth. This is a diagram showing you residence age on a surface in years. So this is 10 million years here, 10 million years, versus oxidation. So this is weathering of meteorites. So in hot deserts on Earth, these red bits, things weather fairly quickly and they weather over the time scale of 1,000 to 10,000 years. In Antarctica, the blue ones, they weather more slowly. They oxidize more slowly. And on Mars, the model is that they're still oxidized, but even more slowly over a very long period of time, tens to hundreds of millions of years sort of thing. And we're going to suggest that meteorites on Mars should be preferred habitats to microbes compared to anywhere else. So this is something for Martin to pick up when he sends his Japanese rover to Mars and picks up silicon nodules as well. Careful these things too. So chemolytic trace gain energy via oxidation produce minerals, and this happens during weathering. They can also induce it themselves, but it's good when they're in a weathering environment. So what would happen to a meteorite sitting on the surface of Mars weathering away? It's got all these starting minerals we talked about, all these reduced components. There's the organics, it's got a particular isotopic signature. Mars has volatiles in the atmosphere, has things like sulfate and chloride, chlorates on the surface. It might have life sitting on the surface. And all those things will go together to produce a final alteration product inside the meteorite that's a function of the temperature, water-rock interaction, salinity, pH, that sort of stuff down there. And it's a function of life, including the isotopic variation. So how do you actually go about researching this? The meteorites on Mars, we can't go and look at them. The point is that meteorite starting chemistry is independent of its planetary residence. So we can go and study meteorites here and have a look at what happens to them, what life does to them, how life interacts with them on the surface of the Earth, to see how they might do the same sort of thing on Mars, perhaps. So Alastair did 3 field seasons with us on the Nullarbor. And Nullarbor is great because there's very little erosion. It's got a residual surface after wind removal of sand. It's very arid. There's salt and clay. There's big humidity swings, which will come into play in a bit. And it's a lot cheaper than going to Mars itself, obviously. That's what the Nullarbor looks like. It's quite flat. All those white rocks everywhere there are white limestone. Meteorites are dark, so they're easy to spot there. So normally when we go there, we find 20 to 50 meteorites over the space of a couple of weeks. So we always find meteorites, and we find a variety of different things too. Turns out that in about 30,000 years, normal meteorites will tend to start breaking down and turning into broken up bits of rubble you can't recognize anymore. So that's kind of the time frame for weathering on the Nullarbor. So what did we find? When you look inside these things, we find a couple of different communities. The first one I'm going to mention is this, what Alastair termed a crypto-endolithic community. What the hell does that mean? basically it's things that are living in cavities in meteorites. So this bit here is a cross-section of a meteorite. This iron oxide domain here is a place where there was an iron metal particle that's been oxidized, and the oxidation process has left a little cavity behind here in the rock. And so inside that cavity, there's things like goethite, which is an iron oxyhydroxide, gypsum, which is calcium sulfate, jarosite in there. These things have good preservation. They can seal in microbes and trap them in the rock. When we look inside those little crypto-endolithic communities, this is what we see. We see microbes living inside these little cavities in the meteorites. We see similar sorts of things in these chasmo-endolithic communities, so things that are living in fractures in the rock. When we break off a fracture from a meteorite, we see things like lots of gypsum and calcite in the surface. And directly on those surfaces, we see microbes living in the fractures. But those veins of carbonate and sulfate look like this in cross-section, and inside those veins are preserved biofilms too. So when we acid etch the surfaces, we can reveal microbes living underneath the surface. So these are kind of like fossilized microbes living beneath the surface of near the freshly forming vein. So there's exhumed biomorphs living beneath the surface of these things. So it's a way of preserving or fossilizing microbes in meteorites. So the same sort of process happening on Mars is a way of fossilizing microbes eating these things. So how do the microbes get in there? This is turns out that when it gets dark on the Nile Water, obviously the temperature goes down, and the minerals that are inside these meteorites are minerals that take in water from the atmosphere. And so when it cools down again, they release water back into the surrounding environment, and that increases the relative humidity. So the humidity inside the meteorites goes up as the temperature goes down. So what that means is during the daytime, they'll absorb water, and during the nighttime, they'll release water. So this is just a model of water absorption and release from the minerals inside these veins. So there's an oasis inside these meteorites that's great for life. Life needs water. So we have a little oasis inside the meteorites on the surface at night. So all those minerals are the ones that absorb water and then release it back in a daytime, nighttime cycle. This is an image of an actual meteorite in cross section in the orientation that it would sit on the surface. So it was sitting at the bottom there and facing up to the sun there. And you can see on the outside, you've got all those bright brown and white specks. Those are the sulfides and metal particles. So that's unoxidized iron, nickel, metal, and iron sulfide. Inside the meteorite, you've got all this oxidized iron oxides. It's porous, it's permeable with the fractures there. It's a great place for life to live and interact with reduced redox reactions. So here's Alastair's model. We've got a meteorite sitting on the surface. It's getting heated up during the day. It's got an internal oasis being developed. Capillary action on thin fractures draws water up from the groundwater and creates this ideal environment inside the meteorites for chemolithotropes to live off. When Alastair's done analyses of what's actually living inside the meteorites, it's things like ferrooxidants, and biologists will know more about that sort of thing than me, but it's basically organisms that live off iron oxidation reactions. So here's Alastair's Mars model. This might be the sort of thing that might apply to Jezero crater, for example. So you might have started off with a time when there was water, ice-covered lake in Jezero crater. A meteorite might have punched through the surface here to end up at the bottom of the lake. And, that'll have a redox gradient in the lake. Over time, that'll dry out, and we develop a series of fractures in the bedrock here that are filled in with those sulfates that we see in the various places on Mars. In the Curiosity images, for example, the meteorite here would have been sort of sitting in this semi-wet, semi-dry environment for a period of time, and that's the time when this Mars model, similar to the Nullarbor model, would apply. So you'd have the same sort of thing. The added thing here is that meteorites provide a place where they're protected from UV radiation. the same sort of humidity oasis would develop as all those hydrated minerals form and that sort of thing. It's very much the same sort of model. Over time, you get weathering and oxidation going on. Micrometeorites would have been accumulating through that whole period. They would have been accumulating from T1 here right through to T3, so progressively adding up more and more over time. So nutrients are in the soil profile, and being great, providing all the nutrients for life, that sort of thing. So that's the sort of place where we think it would be great to go looking for life, not so much picking up sedimentary rocks, but go pick up a meteorite that's been sitting in the lake environment as it's dried out over a long period of time. So we've been pitching a Mars sample return. Part of the mission should be to pick up one of these things and try and take it back. There's Alice does a summary of all the different things you can do with what's inside one of these meteorites. It's too much to read through. But basically, these are some of the takeaway messages. Micrometeorites and meteorites are pantries of bioessential nutrients that you can't really get elsewhere on Mars. They're complex habitats inside the meteorites. They provide water in desiccating conditions by those humidity oases. Life can impart isotopic fractionation signatures that you can recognize as being distinct from the standard of the meteorite, standard composition of the meteorite. And they contain their own distinct communities of microbes that are different from what's in their surrounding environment. They're the most well understood rock type on the surface of Mars because we've studied so many of them over so long. They're probably more likely to have sampled a biosphere if there was one, when Mars was habitable than any other rock because it has the right microbes in it. They last for a billion years on the surface without too much trouble. Similar weathering, but slower, creating hygroscopic minerals that trap Martian volatiles and potentially Martian life. So that's I'll leave it there. That's kind of the main message. And are there any questions? Yeah.
Okay, you got me sold. But we need some numbers.
Yep.
I'll give you the easy one. What fraction of the redness of the red planet is meteoritic apparent on the surface? And it's not been part of, never sunk to the floor, ever just not that. But then, how many grams per square meter per year of tribosite arrives?
That's, yeah, it'd be hard to answer that because we don't know very well how much tribosite is in micrometer.
Okay, let me
Yep.
let me just talk about iron meteorites.
Yep.
And then carbonaceous meteorites and
Yeah.
apologize for the
So there should be a lot. I mean, that you saw from that nullable samples, we had hundreds of micrometeorites in stuff we just scraped up with a broom and dustpan in just a few kilograms of samples. There's plenty of reduced material in those. And then so to answer that question, what you would have to do is look at the infall rate, the age of the surfaces, whether there's been wind adding material or wind taking material away and leaving stuff behind. It will be quite variable across the surface. There will be some places that's very enriched in all that material and some places that's depleted of all that material.
I'll take it order of magnitude. I mean, so you know about the Australian desert,
Yeah.
the relative gravitational levels.
Yeah.
So within that, so how many grams or kilograms of
I-
yeah. So we want to help with a biomass, right? One thing to think of guess as to what. And I guess biomass.
Yeah, I get you. I would be going at probably percent levels, like 1 or 2% of meteorite material in a soil, like that sort of thing. Without having tried to crunch the numbers, it would be, I would guess at about that level. Yeah. Yep.
The photos of the micro living with the that's stunning. But like to me, that reminded me of what they found on the Melankovitch meteorite.
Yeah. Yep.
Like about that, like maybe these structures, and then I was on Alan was being like micro
Yeah, that's a good comment. So the ones found in Allen Hills, 841, whatever it was, they were little trains of magnetite that were tiny. There was only a few tens of nanometers long. These ones are normal size of microbes. They're typical microbe size. They're known microbe shapes and consistent with known microbe types sort of thing. So the ones in Allen Hills where people have sort of put those aside because they're the wrong sort of size and that sort of thing. These are quite different, and probably there wouldn't be too many biologists who would argue against these being microbes of some sort. Just going back to your question, actually, I thought of something else. Lunar meteorites and meteorites from the surface of Vesta have lots of meteorite material in them as well. They're regolith surfaces, and they're, percent levels of material. Yep.
So that process you described on Earth of the humidity and sort of evaporative wicking drawing of the groundwater, and then your model on Mars about a meteorite falling into a lake. If there were lakes, that's probably 3.5–3.8 billion years ago. And it's pretty cold there now. Do you think that same process could still be happening on the surface?
I wonder if there are some parts of the obliquity cycle in some parts of Mars where it might still be relevant. Maybe in the northern plains, and if they're beneath the surface, it might be relevant. Don't know. It's probably not applicable now. But there might be parts of the obliquity cycle that kind of get warm enough in some parts, maybe.
Yeah.
But these,
I think it does get up to 25 degrees at some point
Yeah.
in Mars. It's been liquid water shown here.
yeah. And I guess if you're preserving microbes in fossilized biofilm type things inside these things, that would preserve that for millions of years. Yep.
Is there much nitrogen inside meteorites?
Okay, so if you go back to the most primitive meteorites, the carbonaceous chondrites, they're basically the same composition as the sun, the most primitive ones, and so they'll have the standard starting composition of the solar system in them. I don't know what mineral they would be in. Might be in things like apatite and things like that. I don't really know, but it will be tiny amounts. It wouldn't be a great source of nitrogen on the surface compared to basalts, I don't think.
And consider mechanisms.
I would think that, I don't know much about how much nitrogen there is in the Martian atmosphere, but I would think there'd be more nitrogen in the atmosphere than inside the meteorite. Yeah.
Good. Okay, I think we'll leave it there. Thanks so much, Andy. That was fun.
There the screen is in. Push it. This mic goes resume.
Right, but it's only directional. Yeah, you just got to turn.
Okay, great. Okay, so my great pleasure to introduce our second speaker of the morning, who's got a 20-minute slot, Joseph Michalski from University of Hong Kong. Thank you so much, professor in remote sensing and Mars specialist.
All right, thanks for allowing me to speak about lakes on Mars today. So let's see, am I going to do that? To advance is clicking. Oops. Right.
The keyboard.
Yeah. Okay. Okay. Perfect. So the first slide after this will explain to you what is super special about the planet Mars. Okay, perfect. So on the top left diagram, it just shows the sort of ages of crust that you have in the solar system. If we're interested in the origin of life, we're dealing with what, theoretical models, mathematical models, experiments to a degree, but mostly through geological exploration. So if you just think, in the whole solar system, the most ancient crust that existed when life originated, you're not going to really be looking on the moon and Mercury and that sort of thing, because we don't think that was super relevant. The crusts of Venus and Io and other objects are too young. So basically you're dealing with Mars and Earth as time capsules for exploring origin of life empirically. And on the right side is this diagram showing from modern time back through billions of years, the amount of crust, relatively speaking, of the different planets, Earth and Mars. Now we could argue about the details of this, but let's not. Here are some time markers. I mean, the details of the amount of crust is what I meant to say. It's not that important. The issue is that there's 70% of Martian crust is over 3 billion years old. And so there's a lot more preserved from what would be the Eoarchean or Paleoarchean. And so all these things were occurring on Mars, a lot of seas and lakes, which I'll speak about, hydrothermal activity, and all sorts of interesting geological stuff at the time when life originated on Earth. So it's a great place to look. It's a window into the early Earth. And at that time, we have a lot of evidence now through climate models and through empirical data that Mars had a reduced atmosphere, a greenhouse that contained CO2, but was heat warmed probably by hydrogen and methane. And as a pet peeve of mine, I just wanted to point out that when people draw ancient Mars, they always make it red like it is today, and then they just flood it in with a bunch of water. But ancient Mars probably wasn't so red, if that matters. So in terms of lakes on Mars, you probably understand why they're so important. You have a place to mix nutrients and energy sources with water and so on. And so we know that they existed at least episodically in the Noachian, but the Noachian is 400 million years long or longer. And you only need warming events for tens or hundreds of thousands of years to actually have these ephemeral features exist. So I think sometimes Mars geologists forget that we're not looking at a super long-lived system in a lot of cases. And that's important when it comes to biogenesis. It's not just trapping things that already existed in the biosphere. These things are well preserved because Mars lacks plate tectonics, and they could have wetting and drying cycles. Well, they probably did, wetting and drying cycles. And as those wetting and drying cycles occurred, you'd have small pools with different chemistries and gradients, things like Martin spoke about yesterday that are advantageous for life, things that are described in these two books, which are really fascinating reads if you haven't done it already. And so I think lakes have some of the positive features that hydrothermal systems would have as well. This is a schematic diagram, but we could spend a lot of time on, but I don't have that much time today. So point is that a lot of this juicy stuff that we just heard about would be falling into the lake. You'd have groundwater flow, overland flow. You have the potential for photosynthesis, but keep in mind that we have the faint young sun and Mars is further away from Earth. So when you think about how awesome modern lakes are for preserving matter, for generating a lot of biomass, you have a planet with about 30% of the photosynthetic active radiation available. And at a time when it was 1 billion years before oxygenic photosynthesis existed on Earth. So sometimes when Mars people are arguing that lakes are so great for generating biomass and preserving it, they might have a photosynthetic bias, forgetting that, that would assume that it evolved earlier on Mars, which it may. And so you can trap all kinds of stuff in the detrital and oxygenic sediments within here, and there's a lot of interesting chemistry. So a couple other interesting points just to note is that lower gravity means lower settling time. So lakes would be murkier with more clay and coarser material further into the basin. We didn't have vegetation, of course, out on the plains, most likely. So the amount of sediment mobilized by any given event would be a lot. So you might get a lot of stuff dumped into these lakes. And at this point, actually, I won't spend a huge amount of time on this, but remember with remote sensing, we're kind of looking at major mineral abundances. I'll speak about mineralogy later. We don't know so much about accessory minerals, and those are really important for geologists when we look at bin sections or in the field. Minor phases tell us a lot about the environment and habitability. Harder from Mars. Jezero is super famous, and for this amazing delta. I'm in the camp of I've never been really sold that deltas are the way to go. They can form kind of quickly, and we've seen even here in Jezero that these deltas contain really coarse material as well. So this isn't where you go for trapping of biosignatures necessarily, but still a very interesting site. We found that some of these carbonates and clays actually occur within igneous rocks with igneous textures that have been metasomatized. So there's a story to play out here that is not yet told, but it's a very interesting site for sure. A little bit more on the delta front. Again, they're geologically interesting, and I can understand it's a defensible position that we should go to a lake with the delta because the delta is preserved stuff, but that's really assuming that you had biomass available that can get concentrated from the sort of the catchment into that area. And these are, again, transient features can form in a 10,000 year time span. They can probably form much quicker than that, actually. So I'm not here to bash deltas. I'm just saying that's kind of where we've been led to believe is that's the defensible position for how we choose to land spacecraft where we choose to. So this is about a remote sensing survey of lakes on Mars using infrared reflectance, infrared emission, LiDAR, and so on. And there are these 4 categories of lakes you might consider. The ones that are easy to identify are where you have a channel that flows into a basin and a channel that flows out. So there you can estimate a base level and a lake depth and all that. You also have channels that flow in, but no channels that flow out. And those are closed basin lakes that have, is a little bit harder to characterize. We have some where there are no channels in or out, it's entirely groundwater fed. But if you look at the geology in detail, you can make a strong case. This is McLaughlin crater, I'll show you that one later on. Clearly a lake, but they're harder to identify, so underrepresented. Thermal karst lakes are smaller scale, and those are perhaps less interesting, but important nonetheless. So here's a map of all the lakes that we know about on Mars, over 500 of them, and the closed basin, the open basin, the thermal karst, and so on. I want to get to some of them, be sure I don't forget to get to some of the more interesting stuff. So in terms of reviewing this stuff in a recent review paper, I wanted to point out what we don't know in that paper. So if you look at this size frequency diagram, this is the Earth line, this is the lake area, and here the number of those lakes on Mars. So Mars kind of follows a similar trend as Earth, but we don't know much about the small lakes. There should be many, 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 many more of those. So those would include the thermal karst ones, and maybe they get removed by erosion more easily, or maybe they're harder to find, but we don't know very many about those. What else do we have here? Most of the lakes are Noachian, so that makes them 3.5 billion years old or more. Where we do have some sort of idea about depth, this average depth of hundreds of meters. The ones that are purely groundwater fed are very hard to detect, so we probably expect many, many more of those, but we don't know about them. Large Great Lakes we can find, but those are also underrepresented because, again, the scientific process has been to go for the most obvious cases first. And as we explore more, we'll find more of these other more complicated ones. And a lot of them have been volcanically resurfaced, which is a bummer and just a reality. So in terms of the small lakes, here's an example of what the periglacial lakes on Earth look like. And this is the largest number of lakes on Earth by number. There are just millions of them. But we don't know much about those on Mars. And the ones that we do know of, we don't know if they were sublimation driven or melt driven. Volcanic lakes are interesting on Earth. And so this is Lake Oskia. If you've never been there, looks like that, and it's gorgeous, and it is a very fun place to be in the field. We know nothing of these on Mars. No evidence for them. No one's really looked. It's kind of a death sentence for a grad student because it's very hard to send them on a project that may not work out. So we're not doing a lot of exploration, but there are some sites that could potentially have had transient lakes, but we just don't know much about it. Tectonic lakes on Earth are the longest lived and deepest ones, like Lake Baikal. So we don't know much about those on Mars, and most people would say we don't know of any of them, but actually this one, Eridania Lake, is in fact a tectonically controlled lake system. So it's super huge scale, hundreds, thousands of kilometers across, or 1,000, and 1 to 2 kilometers deep. It would have been long lived for however many years, but probably among the longest lived on Mars. And so there's a lot of volcanism that occurred in the basins, very diverse mineralogy. You see chlorides along the coastline. You have iron clays in the deep basins, carbonates, iron, manganese, magnesium carbonates. And if you look at these scale diagrams showing the volume of water that is estimated for the Noachian, all the lakes combined versus Eridania Sea, it's just a huge amount. So about 3 times bigger than Caspian Sea, 10 times bigger than Lake Baikal. And if you look at the floor deposits there, they're really interesting stuff, totally juiced up and with interesting color gradients that are probably related to chemistry. And from a spectral point of view, we see iron serpentine, we see Minnesotite and chamosite and non-tunite glauconite, carbonate, silica, and there's probably pyrite. You can't see pyrite from a remote sensing point of view. I don't know if people realize that. It's a bummer because we'd like to know where there's sulfides, but it's just dark and opaque and boring. But we can find jarosites. So they, just like in mine tailings, they might trace pyrite currents. So what else do we see in terms of diversity of lakes? So here's again the map. I'm just going to show you some kind of a summary figure. You'd expect, like we do all these analog studies for Mars in salt pans and stuff, but actually we don't see much of that. There's one lake we know of that has chloride deposits, Ahenic and Kelly's. Two lakes, or maybe three that we know of that have a lot of sulfate, and this has kaolinite as well. So that was an acidic lake. These volcanic fractures generated fumarolic gases in the lake and so on. So acidic lake here. We see carbonates in a number of cases, but they're probably much more common than we realize. They're just not super abundant. And so my student now has a paper showing another 10 or 20 of these, but carbonates are pretty common. Iron clays are pretty common. This place in McLaughlin has really interesting stuff. I'll show you another slide just on that. And Gale crater, of course, in the very bottom of the crater, you have these magnesium and iron clays in things that look like lacustrine sediments, but it's really debatable, in my opinion, as you go up. The rover spent years and years exploring this mound of stuff with cross-bedded sandstones, and I just don't buy it that it's all lake sediment. It's not convincing to me, so got to watch out for aeolian processes and airfall as well. The floor of McLaughlin contains these awesome exposures of stuff. I mean, look at these textures. So there's a little bit of a scale. It's a big cliff face, about 100 meters high, and really cool convolute sort of structures. And the material within here is serpentine, iron clay, and carbonate, and oxyhydroxide as well, something like ferrihydrite or something like that. Pretty interesting stuff. We're absurdly long paper about it, which had to be upsetting for the reviewers, and God bless them. So just to summarize, here's a diagram where, again, happy to debate these kinds of things over coffee or beer, or how this should be conceptualized. But point is, there's not a huge record of ancient lakes on Earth. The oldest one is about 2.7 billion, as far as I know. And here we have a lot of ancient lakes on Mars that are sort of Dead Sea Scrolls for the inland waters that would have occurred in the Archean, but it would have occurred before epigenic photosynthesis, but maybe at the time when you had other forms. And we have some missing lakes from the middle of Mars history. We don't know a lot about the small ones. We don't know about volcanic lakes. There's a lot we don't know. But they certainly would be interesting sites for mixing the fluids. We just don't know much about whether we should assume photosynthesis occurred and whether that biases our view of what to expect. So this is the last slide. And again, I think that these are certain lakes, not all of them. So to be sort of Orwellian about it, all lakes are equal, but some are more equal than others. And we have to consider that when we're choosing sites for sample return. China is planning to send a sample return mission to Mars in 2028 or 2030. And McLaughlin crater is one of those sites. There are some other ones. So let's have a chat. We have time for questions. This is a painting by Bill Hartman, by the way. You don't have questions, I do. Okay.
You think it's possible that any of these lakes may have frozen and then been covered over with wind blowing dust, and will I still preserve and not be able to see them?
Okay, so I didn't even mention the paper about 3 potential lakes in the South Pole. So those were detected with radar sounding. And of course, you know how radar works, you probably do. You have a discontinuity effectively, reflector. So there's a dielectric constant contrast. And My personal feeling about that is that the saline lakes are the easiest explanation. Some people think it's the hardest, but the thing I don't understand is that there are 4 papers that say no way, no lakes, they're clays. But I don't know, like that's easy to say, but because the dielectric constant of clay might be sufficient, but you don't have 100% clay in anything, mostly. So I don't know how much of it you need and what the geological process would be to have these lenses of pure clay. Like a lens of salty brine is not any harder to explain, I guess, from my point of view. So those are actual evidenced examples. Other cases, but I think throughout history there would have been a lot of ice cover, uncovering. What's the one in Canada, Pingalute or something? There's an awesome crater lake in Canada, but it's in granite, so there's not a huge amount of sediment in it, but it's been frozen over through ice ages and it's been long-lived lake. I think whoever you guys can manage. Sure.
It's latitude lakes. Have you had a look to see if they're correlated with any other morphologies that are potentially related to like groundwater, alluvial systems like gullies or RSLs or any of those kind of things?
I think I missed the first part of the question for the which types?
Mid-latitude.
Mid-latitude.
Yeah.
Yeah, so the ones that have channels in and out, sure, they're kind of the easy ones to detect. There are, like McLaughlin has goalies inside it that all terminate at a similar base level. So they did form from some kind of snowmelt or precipitation of some way. But RSLs are generally young phenomena. So there's not an obvious correlation most of the time.
Yeah.
Others? Yes.
Question about the volcanic lakes that mentions that you don't know yet.
Mm.
What's the information that you're hoping to find in volcanic lakes that you can't find other types of lakes? I never thought about this.
Well, I mean, there's nothing super special about them except that you would assume there's, depending on the age difference between the magmatic activity and the lake, there would be an obvious heat source for lake floor hydrothermal systems. Yes.
Actually, related to my question, you found that acidic lake, right? Like the carbonate and
Other authors did, but yes. Yeah, James.
so like I expect that to me is like saying you've got like is there any sort of like other evidence you found for well not you anyone that you know of like more widespread
There's a lot of acidity, and it's not. Okay, I don't consider myself a geochemist, but pH and alkalinity are not coupled all the time in a Martian model, right? So we see a lot of evidence for sulfur-rich stuff and minerals that are typically common in low pH environments, but not all that stuff is in lakes. The lake environments are pretty rare.
We're gonna have to cut it there.
Okay, cool.
Thanks, Joe.
Thanks.
See the Zoom again.
Did you want to log in on Zoom or just?
So I'm logged in, but I don't know if it.
Oh.
There you go.
Yeah. I can see. Did you see the meeting link?
No.
It's maybe I can send it to you again, but we can just, it doesn't matter. You go in.
Can I get it here on the yeah, here's the meeting ID. Are you on Zoom?
Yeah.
So it's 825
Mhm.
1674 3620.
Oh, yeah, I see it. Let me log in.
You log him in and make him a presenter.
You don't want to.
Okay.
Is that the right screen?
We see the presenter view.
Great. My great pleasure to introduce Simon George, our next speaker, Emeritus Professor from Macquarie University and organic geochemist extraordinaire. Thank you.
Thanks, Martin. Hello, everybody. I'm going to talk today about massive manganese carbonate deposits and their effect on the biogeochemical cycle in the Cryogenian interglacial. And I'd like to first thank Jai Ai and Sandra Sjöström, who made major parts of putting this talk together. It was part of Jai's PhD. Quick summary of the talk, to start with. Detailed petrography and geochemical analyses were carried out to reassess biogeochemical pathways in regulating the formation of black shale-hosted microorbital manganese carbonates deposits in South China. And this study, we think, sheds light on the global Neoproterozoic post-glacial carbon cycle under quite specific atmospheric oceanic conditions. So we worked in the Nanhua Basin. This is a map showing the sedimentary lithofacies, the paleogeography, and the paleobathymetry during the glacial deposit of the Nanhua Formation. This is late Neoproterozoic. You'll see that there's quite a bit of variability in the thickness of the basins. It's fault controlled. And we worked at this location over here, Qiannan. This is the sedimentary section across the basin for the Nanhua, from northwest on your left to southeast on your right. The things to note is we worked in this area, the Datam Formation, and below it are Sturtian age tillites, and above it are Marino age tillites. So this is definitely an interglacial deposit. This is a stratigraphic column of the ZK0408 borehole from the Qiannan area. We worked at the base in the unit 1 of the Datam Formation. We got some black shale samples and also some pretty manganese-rich samples shown in red. And we also had some samples from a mining block. And as I said, the Sturtian glaciation is represented before by this formation, 663 is the boundary, and the Marino glaciation is up here, boundary 654. These are hand specimen photographs of Cryogenian interglacial lower member Datam Formation. And these are both manganese carbonate ores. On your left is a laminated type with a texture that's quite distinctly laminated. And we call this the type 1. And on the right is a much more massive type of manganese carbonate ore. We call these the type 2s. We see amazing gypsum in places, calcium sulfate, with radial fibrous fire-like structures. And these are mainly in the laminated type 1 manganese carbonates. This is a SEM photomicrograph showing manganese carbonate crystals with spheroidal shape. Diameters of 3 to 5 microns for these type 1s. These are backscatter SEM images of the same sample. In OR is the organic ring and MC is microcavity. They're microspherulitic microstructures with radially concentric microfabrics. And the rings of organic matter are associated with specific laminae. And lastly, there's some gas bubbles, which you can just make out probably in this picture, in the middle of some of the manganese carbonate grains. This is an organic petrography photomicrograph of a type 1 carbonate.
In this, the organic matter is shown as this rather diffuse grayish yellow color, as well as these organic rings I mentioned before. You'll also note there's a bit of pyrite in the sample. These are SEM element maps for manganese, for calcium, and for carbon. The things to note from these is that there are calcium-rich cores of these carbonates, and they are coated with a kerogen ring. You compare the carbon and the calcium. There's a manganese-rich layer, which is made of rhodochrosite, which coats the kerogen cavity ring, and in turn is coated by an outer layer of calcium-rich rhodochrosite. The manganese microspheres generally cluster together to form amalgamations with diameters of 20 to 50 microns. And most of the organic matter, which you can see on the right, is likely to be an organic residue after some oil cracking. So in contrast, the massive type 2 manganese carbonates look a bit different. They're smaller. The scale bar here is 5 microns, so this is less than 2 micron grain size. And they have short rod shapes, smaller rhombus-shaped, scaly type texture, which you can probably make out just here. Backscatter SEM again for the massive type 2s. They generally have a more simple core shell structure instead of those multiple cycles of growth banding, which is spheroidal for the type 1s. In some of the sections, the calcite or manganese calcite cores are surrounded by calcium carbonate, but other times they're surrounded by silica. And this is in cathodoluminescence, which shows that the fine-grained rhodochrosite has a reddish-orange luminescence color, whereas the calcium carbonate cores do not display bright luminescence and are highlighted in this photomicrograph by the yellow dashed circles. These are SEM element maps for the type 2s. The organic matter, which is shown over here in carbon. Oops, sorry. Up here, this is the carbon. This organic matter fills in the intergranular pores of the grains or is around the aggregates. So we did a bit of time of flight SIMS iron work at the Swedish RISE Institute. And this is for a type 1 manganese carbonate. The things to note is that we have some organic signals. This is CN minus over here. We have CNO minus, C3N minus, and C2H minus. And if you compare the distributions of signal for these compared with the manganese, you'll see there's quite a close correspondence, but there's quite a bit of difference compared with the silicate signal. So there's a localization of the organic matter with the manganese carbonates. We did some inorganic geochemistry. These are PAAS normalized trace element distributions. For on your left, the manganese-rich black shale, and on your right, the adjacent black shale that doesn't have high contents in manganese. The things to note are high enrichments of cobalt and strontium and molybdenum in the manganese-rich ones, whereas the adjacent black shales are characterized by higher molybdenum and uranium and vanadium. So some differences between these. Here we have similar distributions, but this is for the rare earth elements. Again, on the left, the manganese black shales have a bit of an extra amount of cerium, positive anomaly of cerium, which we don't see in the adjacent black shales. And there's also a bit of a European anomaly. The cerium over cerium star is in that range, averaging 1.24. This is a cross plot of the cerium and praseodymium ratios. For in red, the manganese-rich black shales from this study. In blue, the adjacent black shales. And other data from published data in yellow and grey. You'll see that there's a positive cerium anomaly for the manganese-rich samples, which isn't the case for these adjacent black shales. And this is adding the data from the literature, especially from De Prutter et al. 2018, and showing the relationship between the cerium ratio and the total amount of manganese in the sample. So you see there's a positive correlation between manganese content and the positive cerium anomalies. And we think this may have developed during initial manganese precipitation processes by oxidation of the cerium by the manganese oxide or hydroxide, and or absorption of cerium-4 on the surface of manganese oxide or hydroxide. There's also an interesting correlation, which we add a little bit of data to, about the cerium anomaly compared with geological age, here from 4 billion through to present. Most of this data is from Maynard 2010. Our data is in red, just in here, which is contributing and showing the same sort of trend. The major thing you can notice here is an increasing spread in this cerium anomaly of manganese ores through geological time. And this is perhaps due to increasing the oxidized state of the Cryogenian interglacial, which typically gets around about 600 million years, and progressively more diverse biosphere at this time. This is a cross-plot of rare earth elements, this time looking at the europium anomaly compared to manganese weight percent. Again, the manganese-rich black shells are plotting up in this zone with this higher europium anomaly, which has positive correlation with manganese content. We did a bit of isotope work as well. This is a cross-plot of del-13C of the carbonates on your y-axis and del-18O carbonates on your x-axis. Our data is in the blue and the red, and there's some literature data also plotted. The things to note are that the manganese-rich black shales have a slightly more negative carbon and more positive oxygen than most of the adjacent black shales. And this is especially the case for the type 1 manganese carbonates. We think this was likely due to a contribution of dissolved inorganic carbon from oxidized organic matter, a humus colloid or EPS, after burial in anoxic sediments. So now I'll bring together some of these observations in some models of what we think was going on during the Sturtian deglaciation period. This is the post-depositional pathway for the type 1 manganese carbonates, showing a stratified lake with a barrier through to the open ocean. The type 1 manganese carbonate is interpreted to be a microbially mediated metallogenesis product, during which process the organic matter played multiple roles, including catalyzing the manganese redox cycling, transporting preformed manganese oxides, and serving as a carbon source. There was a process of the humus coming through on the slope section and being coated with carbonates, forming these observed calcium and manganese carbonates that I've mentioned, the growth banding. In contrast, the type 2s have this sort of thing going on where there's calcite precipitating in the water column of this restricted basin. It's a more physiochemically forced formation pathway. And then those relics of the primarily precipitated calcite served as the nucleation sites for manganese-rich carbonate precipitation. There's a general decreasing amount of TOC with increasing manganese content. So here's TOC, manganese, generally going in that direction. So we think that the microbially mediated manganese carbonate formation was at the expense of organic carbon during early diagenesis. So this was not favorable for organic carbon preservation. There's a positive correlation between manganese and the enrichment of phosphorus. And this can occur during massive precipitation of manganese oxides during the pulsed oxygenation events, probably linked to injection of oxygen-laden surface waters. So here's a summary of the biological carbon pump And phosphorus recycling, this for the type 1 carbonates. We think this is a microbially mediated diagenetic pathway, which happened soon after Sturtian glaciation. This converted organic carbon to buried inorganic carbon and prevented recycling of CO2 derived from organic carbon respiration from diffusing back to the atmosphere. So there was less efficient regeneration of phosphorus due to orthogenic calcium manganese carbonate precipitation via the manganese oxide shuttle. And this happened under the pulsed oxidation events, probably constraining primary production in organic carbon burial. And this limited the rapid accumulation of atmospheric oxygen. In contrast, the type 2s were orthogenic formation under a more reducing water column, and this favored the burial of organic carbon and higher primary productivity fueled by the efficient phosphorus recycling. Our conclusions. Type 1 manganese alluvial carbonates formed through microbially mediated manganese redox cycling under relatively high PCO2, coupled with density flow that injected oxygen-laden surface waters into sediments at the early stages of Sturtian deglaciation. The type 2 manganese carbonates have a comparatively smaller grain size, relatively simple core shell structure, not necessarily due to organomineralization. And we think the large-scale sedimentary manganese carbonate deposits could serve as a particular storage of inorganic carbon and a supplementary retention of phosphorus, which could have regulated primary production, organic carbon burial, climatic conditions, and the extent of atmospheric oxygen accumulation. So we recently published this just a few weeks ago in this Pre-Cambrian research paper. I want to acknowledge the major contribution to this work by Jia. This is a picture of her at the Tofsums instrument in Sweden. And this is my last slide. Thanks for your attention and any questions.
See the manganese carbonates, these equations that develop that.
Yeah, that's a good question. I haven't worked on those specifically to look for manganese carbonates. I've only done this particular study in this basin, so I don't know. But other people have published work, and there are some in some other basins, yes. But that's published literature, not our work. Yes, ma'am.
What are the implications for the complexification and evolution of life?
Well, I think these sorts of environments were where there was plenty of nutrients, plenty of oxygen being generated with this deglaciation happening. So it was quite specific conditions, and this may have been the thing that drove biological evolution. So these big changes in the oceans and in these sort of marginal basins may have. That those big nutrient fluxes may have been the thing that, or something that contributed to the moving of biological evolution.
Okay. One more. Sure.
How do you explain the high concentrations of cobalt in the manganese, which is not because we work on pyrite chemistry a lot, and quite often we notice that periods of high oxygenation, we see less cobalt than vice versa. And we always think that it's because when you have high oxygen content, you're forming more manganese oxide. And that's a huge sort of boost for cobalt in the structure, and so that prevents cobalt being available with on the pyrite. I think something is going on there.
Yeah. Yeah, it may well be. I'll have to think a bit more about that. I don't know so much about the cobalt partitioning, so that would be an interesting thing. I'll have to talk to Jai about that.
Anyone see the pyrite in the shell?
We didn't, and I'm not aware of other people who have done that. No.
Okay, thank you very much. Not sure that that's sharing,
Yeah, he's still gonna shoot.
right? It's still sharing.
Yeah, you gotta share again. Yeah, okay.
Okay. Very good. Okay. There we go.
Okay, thank
And
you.
our last speaker for the morning, Qiannan, thank you so much.
Thank you, Martin. Thank you, AS, for offering this chance to me to share our research here. I'm Qiannan from China University of Mining and Technology, and now visiting at Macquarie University. Today, I'd like to share some evidence of carbon cycle recognition in marine ecosystem initiated by the Milankovitch boson during the Early Cambrian. Firstly, I'd like to share phenomenon which enlightened me to my research. It was reported that during the pre-Cambrian to Early Cambrian, the Siberia Basin is here, and which has a total organic carbon about 9.5 to 12.9%. The Arboreal Basin, which has a total organic carbon content vary from 3 to 15%, and the Sichuan Basin, which has a total organic carbon range from 9.5 to 7.6%. They all deposit a high total organic sections, so as being unsought rock. Coincidentally, that we find evidence of mass distinction of small shell bearing finers at sections in Sichuan Basin diffusely. This section is at the bottom of the Chengdu Formation, which was deposited during the very early Cambrian stage. And this is why the boil events happened could be due to the polar climate change, such as the particle pressure of the atmospheric oxygen change or the oceanic condition change. As a part of carbon cycle, organic matter accumulation in the core system can be significant. So we select a set of backhaul samples which pass through the Chengdu Formation at the southern western edge of Sichuan Basin for analysis of the oceanic condition changes. And according to the paragraph that it shows here, this is our position that we try for the samples detection, and because that we can see this position is very near to the pre-Euclidean regions at the very early Cambrian. So Milankovitch boson is, as my presumed declude for traveling oceanic condition change, was also be conducted. This is the whale's position. And let's have an overlook about this whale. This whale is named the Zhaodi at Yunnan province, and the depth of it was from 1,330 meters up to 1,016 meters. And we can see that it has two high total organic carbon zones in this fossils, which is from a very high position at nearly 1,300 meters, and nearly at another is at 1,200 meters. And let's have a look at the lithology. The lithology changes from bottom to up is totally from the argillaceous silicitor to the molybdenum to the argillaceous silicitor and to the silicitor again. It means that the green size from a bottom to up changes from a fine to relative coarses and to fine and to coarses again, which interprets that the thin level fluctuations exists. So we use frequency analysis based on the gamma ring data logging from this wheel to conduct Milankovitch cycles. After robust examination of the background noises and the signal detection in depth series, 4 interface signals, which corresponding to the Milankovitch cycles, were examined. And the first section is about 46 meters. The second group is about 38 meters, 33 meters, 25 meters, and 20 meters. And the third part is about 16, 13, 12, and 9.9 meters. And the final part is about 2.6 meters. According to these ratios and combined with the sedimentary rates that we have conducted by simulation almost for 2,000 times, and it was reported 4 Milankovitch cycles. It was as 2.4 million years, 1.2 million years, 205,000 years, and 1 to 5,000 years. Then we conduct Milankovitch cycle signals using filtering as a frequency and compared with the total organic carbon changes for this year. And we can find this blue one is about 2.4 million years signals, and the red one is about 1.2 million years signals, and the other two, that's green and yellow, is about 1 to 5,000 years, and the green is 405,000 years. Then we can see the red one has closest relation with the total organic carbon shifts. So I use each 3 neighboring points of the total organic carbon contents for calculating the TOC fluctuation slope, which a positive number followed by a negative number means total organic carbon convergence arc once. This is the result. The result shows that 4 convergence arcs during those 4 periods, which is period 4, period 5, period 6, and period 7. Especially, we can see that there is 2 of the points the convergence happened at the period 5 and period 7 cycles respectively. And then I use the again geology chemistry analysis for conducting the oceanic chemistry condition changes. Firstly, that we can see we use the enrichment factor of urine for processing redox conditions for sequence. So it was shown that twice drifts from the digestate to oxide and to dioxide to oxides, and we're using the ratio of strontium vs copper to process the polar climate change. The storage is related to the salinity in ocean, which could be in high salinity due to a dry and hot climate, while in lower salinity for warm and humid climate. Copper has a lower dissolved amount in solvents and prefer to dissolve at very early digestive period. It shows 4 time drops from the bottom to up. And it means that the polar climates might be changed from a warm to humid and to a relative hot and dry again for 4 times. And then we use titanium vs aluminum to process the digestive salts, since the titanium and the aluminum are exclusively derived from the pterogenesis sources, and the titanium normalized by the aluminum could represent titanium bearing heavy mineral contents and concentrates, which could from the pterogenesis detrital materials and could be stable during the weathering and the digestive process. This ratio shows they have 2 drifts from the relative small number and to a high small number. And the last part is about the sea level fluctuation. We use delta theory to process the sea level fluctuation, and it can be seen. It shows 3 drifts from the bottom to up. And more details would be talk about the redox condition process. Basically, urine could be derived from the crust or ocean, and urine have hydrophilo states in sedimentary and hexaphilo states in ocean in seawater. The amount of urine deposits in sedimentary pore depends on the amount of hydrophilo states lost by being transported as a hydrophilo states and feed to ocean. So it's in a very high, it will be moved very high and lost a large number. So it can be seen in a hypoxene or oxine condition. Hydrophilo states, which is in type of urine iron, could be existed stably, while hydrophilo states is oxidized as urine iron normally. But in the ocean, in an acidic situation, which means it has a lower concentration of the oxygen or non-oxygen in these conditions, and part of urine from ocean was reduced as hydrophilo states and deposits in sedimentary and preserved, and making a small amount of urine that was removed. So we use aluminum to normalize this urine and use PAS for calculating the enrichment factors, and based the Pearson correlation analysis, redox conditions have so this is the equation that we used for process the redox conditions. It can, based on the Pearson's correlationship analysis, we can find that the redox conditions of the process have a highest coefficients with the TOC, while other processes like polychemists and the Telger's input and the synapse fractionation has a lower coefficients. Then we use delta theory that we have talked about. It has a straight jet from this hole, and it can be processing for synapse fraction since the reduction based on the delta, the reduction interfaces in ocean mostly just controlled by sea level, and Synchrony changed from the triphilo states to hydrophilo states since the oxygen concentration drift in ocean, and the hydrophilo states of Synchrony could be deposited, while the triphilo states of the Synchrony could be deposited, while the triphilo states moved within seawater. In this case, the Synchrony drift requires reduction interfaces drifts, which is depend on the synapse fractionation, compared with the delta Synchrony drift in this sequence. Just like the left picture that we can see, for the blue curves, you can be see very high strong signals at the bottom of this wheel, which has which holds the two high total organic chemical nanostones. And from the first section, it means the first fractionation of the sea level. We can see it spans almost one round of the 1.2 Milankovitch cycle. And for second sea level fractionation, it spans almost 1.2 round of 1.2 Milankovitch cycle. And for the half of third fractionations, which means it just goes through a regression of the seawater and nearly spend a runtime of 1.2 Milankovitch cycles. And up to these three fractionations, we can see 2.5 sea level fractionations, expand, and after that, it has a mineral, totally organic carbon condensate drifts, and it can be shown that has a lower relationship between the sea level fluctuations and 1.2 million year Milankovitch cycles. So here's our conclusions. The total organic carbon contents of early Cambrian whale samples have two maximum. Reduction conditions have highest coefficient with total organic carbon, while sea level process ranked second. Apollo climate processing ranked third, and the Terry-Jones input processing has only a mineral relationship with total organic carbon. The 1.2 million years Milankovitch cycle is strongly related to total organic carbon fluctuations. It leads to sea level fluctuations, which control the redox conditions. So finally, we propose that Milankovitch boson could be a trigger for change of the oceanic conditions and lead to the organic carbon response as a conference. Okay, thank you. This is all my content.
Thank you. It's a huge study. Any questions at all? We think about astrobiology and our broader implications. We've heard a lot about Mars today.
Yeah.
Do you think that there would be any relevance to understanding deposits on Mars? Do you think?
Since we have used so much like geochemical methods and to process conditions like ocean, water, and for today or 3 of days, we have so much research about Mars, and Mars have also water and oceans, lake and ocean, and might be this process could be used for that, but also it might have some similarities between the organic carbon cycles from the early Earth compared with the Mars. Yeah, they might have some similarities.
Do you think Mars has Milankovitch cycles?
Yeah, I don't know, but yeah, it might be, but maybe the different numbers, because for Earth it's 2.4, and people have conducted so many periods of 2.4 and 1.2 and 2 and 4, 400, 0 and 5. But maybe for Mars and Venus, it have different number of Milankovitch cycles. Yeah, yeah.
That's a good question. So, I don't know enough about this, but there's obviously Mars fluidity changes. There's all sorts of things that happen to Mars that don't happen to Earth in terms of time scales. So how often is a cycle, whatever cycle principle compared to other sort of orbital perturbation of Jupiter interactions? What time scales are those? How they interact?
I mean, it's a different time scale compared with the Earth to the other planets.
Yeah, I get the impression that I don't know about this.
Yeah.
I'm being told that so Earth's not changed its liquidity because it has a big.
Yeah.
Story. So the point is that seemed to me that would be a traumatic relationship which would provide something maybe it's.
Yeah.
But I just don't know anything about it, so I guess that's not asking for a general introduction to this area.
That the method we use to conduct for the Milankovitch cycle for the very early Earth from very early samples, we just use gamma rates logging, where it was means that we use some reduction data, and this reduction methods is from some elements like the urine and others, and they can be absorbed to some small scale size grains, and this is because for the very early ocean, from the very early Earth, it was deposited in a ocean system. But in the other planets, it might be not totally from the ocean system, or it has land and ocean and a lake. And if we can get some different types of elements, and maybe we cannot get a valuable information about the gamma ray data, so we cannot throw this way to get the Milankovitch cycles, but we can use other methods. We can try to find other methods for the objections to conduct the Milankovitch cycles.
Yeah, we can talk more about this over coffee. There are, of course, different factors driving those Milankovitch cycles. Some of those are planetary conditions, like the wobble and the obliquity. And then there's the larger influences of the other orbiting planets. So probably on Mars, you could calculate some of those orbital parameters and the effects from the larger other planets. But yeah, in terms of a depositional record on Mars, it's probably harder to be able to define. Okay, so let's have a break. We've got, I think, 30 minutes for tea and coffee back outside downstairs. And then we'll come back for 11 o'clock for Dr. Benner's keynote this morning. So thanks to all the speakers. pleasure to introduce Professor Steve Benner, who's come all the way from the east coast of the US via California and Hawaii, and then on to Europe on a speaking tour around the world, as I'm sure he does for a lot of his life. Steve Benner is a distinguished fellow at the Foundation for Applied Molecular Evolution, which he founded after serving on faculties at the University of Florida, ETH Zurich, and Harvard. His research has helped initiate several fields, including synthetic biology, paleogenetics, dynamic combinatorial chemistry, and evolutionary bioinformatics. Professor Benner's interest spans synthetic, planetary, and systems biology, chemical genetics, paleogenetics, and the connection between natural history and physical sciences. He has worked with NASA to develop methods for detecting alien genetic material, and his group has also worked to identify molecular structures that are universally likely to constitute biosignatures. Not a bad resume, and clearly one of the deepest thinkers in the field of origin of life and evolution. Just a quick story about my connection with Steve is we were both invited to a little conference in Germany, much like this, about the size of this, looking at early life signatures. And I had just come out of the field from the Pilbara and had discovered features that I'm going to take Steve and a small group to see in a couple of days' time, which was in the very old rocks, we found this layer with concentrated boron in it. It's a little thin tourmaline crust. And we had only just discovered this. It was completely unexpected. We had no idea of the significance or the meaning of it. And I was in the audience as Steve was talking about the importance of boron in prebiochemistry. And I seriously almost nearly fell out of my chair because it was like one of those aha moments that, oh, this site we've been working on to sort of study the habitats and the sort of biogenicity of life may have much broader implications in terms of chemical systems and environments that are able to concentrate some of the elements aside from CHNOTS that could be important for developing life. And it was also one of those periods where I became aware of the fact that searching for extant life in terms of habitats versus the conditions required to make life may not necessarily be the same thing. And I think the community is now much more aware of that sort of thing. And now it's several years later, but we finally have had the chance to have Steve come and talk to our group and come see some of the stuff in the ancient rocks and hopefully have dialogue with all of you about thoughts for the origin and dispersal of life through the solar system and perhaps the universe. So Steve, thank you so much for coming all this way. And it's my delight to hear you today. So I think
I'm going to use this keyboard and I'm on hot mic, so be careful what you say about the prime minister.
Okay, thanks.
Right. So yeah, that was actually quite a remarkable meeting, actually. And I'll get to the boron and tourmaline in just a minute, but I'm not going to talk about much of what we do in the laboratory except in this top wedge. We'll talk a little bit about the paleogenetics, where you're taking what you see out there in the natural biosphere today and working yourself backwards. Matt Baker yesterday gave a very good talk and summary of this. Well, not talk much about synthetic biology either, except at the very end. We'll talk nothing about exploration, I'm afraid. But we are going to talk about the origins of life, and we'll start with the modern world, because the modern world is what gives prompting to this so-called standard model for the origins of life on Earth. Now, like much of what we teach about standard models to our students, a lot of this is fiction, but the idea here is that Darwinism begins with RNA, ribonucleic acid, that is able to catalyze the template-directed synthesis of RNA with replicable errors. And so the idea is that you can make copies of yourself with mistakes, where the mistakes themselves can be copied, is sort of the kernel of Darwinian evolution, because if you put natural selection on top of that process, ostensibly or arguably, you can gain all the properties that we see and all the properties that we value in biological systems. And this actually was first suggested in 1962, that RNA might do both catalysis and genetic information storage in the origins of life. And there's a bunch of reasons why we sort of think that. One, of course, is as an example. sort of an example from Phil Holliger, which is this molecule up on the right, which is an RNA molecule, which sort of catalyzes the template-directed synthesis of RNA. Sort of is because it's not a very good catalyst and requires a lot of magnesium, and I'll talk to you a little bit more about that later. But the better example, which is coming actually from working backwards in the tree of life, is you certainly have all modern organisms are representing, contained within this RNA catalyst, which is the ribosome. That's the RNA molecule that makes proteins. And this is one of the arguments that because it's everywhere, it was present in the last common ancestor. And therefore proteins are made by RNA, so that RNA comes before proteins. So it does sort of solve this chicken or egg problem. RNA makes proteins, proteins make RNA, but the problem is solved that RNA can also do catalysis like proteins. But it also explains these RNA cofactors that are central in your metabolism. I have put a 1-a-day vitamin pill bottle in front of you. Ever look at the recipe or the label on the side, you'll see you have niacin and riboflavin and a number of other molecules. And for those of you who haven't studied metabolism, these are actually all parts of RNA cofactors. So you eat the vitamin, you make the RNA cofactor. And then with niacin, you do, and riboflavin, you do a lot of oxidation reduction chemistry in your body. And the argument is that that's a vestige of the time when RNA was doing all the catalysis in your body as well. So that's great. So all you got to do now is make a 100 nucleotide long RNA, and the problem is done. We can go home, okay? And by the way, that molecule from Holliger is a little bit shorter than 100 nucleotides. So we have to get out of prebiotic soup RNA molecules that are 100 nucleotides long. And you heard it's important to have homochirality. That's a big issue, but we'll talk about that in a moment. So let's start with the geology. Okay, there you are. We are going to tell you that life began on Earth about 4.3 plus or minus 0.05 billion years ago in an environment that had rocks which had a phthalate magnetite quartz redox state. That means there's FeO, which is Fe plus 2, and Fe3O4, which is roughly Fe plus 2.67. This actually is work that's been done by lots of people, but I have a particular affection of this paper from 2011 from Dustin Trail, where he is looking at these old zircons, which are capturing their local environment. He's looking at the ratio cerium 4 to cerium 3. You heard about that in the last few talks, to try to understand the redox potential of the melts from which they crystallize. He actually makes in his lab melts of this stuff and puts cerium ratios in and crystallizes zircons out, and then tries to use that to calibrate the crystals of zircon that he gets from a lot of places. And of course, the best place for the oldest zircons is Jack Hills here in Australia. So that's the story. That means, of course, if the rocks in the mantle are at this equilibrium constant, that the atmosphere has got a lot of carbon dioxide, a lot of dinitrogen, a lot of hydrogen oxide, that is water. This is what we call the redox neutral atmosphere. That means that hydrogen is coming out as water, not as H2. Carbon is coming out as CO2, not CH4, not methane. Nitrogen is coming out as N2, not NH3. And sulfur is coming out as SO2, not SO3, so like Venus today, and not as H2S, primarily. And then you have various energy sources. I have just here showing you the nice picture showing the lightning discharging above an active volcano. But there's also silent electrical discharge, and of course, there's a lot of solar energy. So now what we're looking for is what we call privileged bespoke chemistry. This is chemistry that could not have happened in that environment, okay? So for example, we go to take that environment and say, what organic chemistry did not happen in that environment? Well, there's carbon dioxide in the air, there is H2O in the air, there is solar energy, as well as energy from the other sources that I just mentioned. And these are making compounds like formaldehyde, which is the compound at the top right here, which is a 1-carbon species. Actually, Jim Cleaves has published a very nice paper on this. It's amazing as to what you can say about a species which contain just 1 carbon, 1 oxygen, and 2 lousy hydrogens. But this is actually a paper from Jim Cassidy, Sonny Harmon published this. And what you're seeing here is that if you look at the ratio of an oxidized carbon, that's carbon dioxide, and a reduced carbon, that's methane in the atmosphere, you get a large amount of formaldehyde being formed by a process that involves these species. And this number is sort of quantitative. You get about 10 to the 23rd molecules per per meter squared of surface per year. So that's about 1/6 of a mole. That's actually a substantial amount of organic carbon. You also get some glycolaldehyde. These are for the geologists. This is sort of like taking the course where you're forced to name. They give you a box with 38 rocks on it, and you can pass the course only if you can tell the names of them. We have this in chemistry as well. This is glycolaldehyde, never mind 2 carbon atoms, 4 hydrogen atoms, and that number is not correct. It is 10 to the 23rd minus 6, because this is being made 1 part per million of the amount of that is being made. And so these two things cross at that point. That does not mean that you're making the same amount of glycolaldehyde as you're making of formaldehyde. That means you're making 1,000,000 molecules of formaldehyde for every molecule of glycolaldehyde. But these two compounds could not have been present on the early Earth. And there's going to be some argument within an order of magnitude if the sun is more active, like Vladimir Arapetian says, or less active. And so that's a discussion, but that's basically the case. And so that's actually important for some models of this. This is actually a model from Clowney et al. And this is from John Sutherland's laboratory. They are using glycolaldehyde. There's 2 carbons. By the way, for those of you who have not taken organic chemistry, we don't write carbons. We just put a little bend in the line that says a vertex, which is a carbon atom, and then we fill up the rest of the 4 valences of carbon by hydrogen atoms. That's this 2 carbon atom. They need a stoichiometric amount of this to make 1 ribose. And in fact, the reason why Sonny and Jim did this plot was because Jack Shostak, who works with John Sutherland, wanted to know whether there was enough glycolaldehyde coming out of the atmosphere to support this particular model. And the answer is no, there's nowhere near enough. And it has to be acting stoichiometrically, and you're not getting stoichiometric amounts of this material. So now the question then becomes back to you. So you can't have you cannot not have these molecules in that ratio, if I can just get that number corrected. But the question is, what could not have happened to these molecules? And actually, Harman gives you 2 choices that they could have been incorporated into particles or dissolved in rainwater, but there's a 3rd choice. And now if I were actually giving a course to organic student, who here is an organic chemist? Raise your hand. Who calls themselves a geologist? Raise their hand. Who calls themselves a biologist? Raise their hands. Who calls themselves a physicist? How about computer scientists? Oh my God, I'm in trouble here. All right. So yeah, so I won't give you this test, but I will tell you that if you have sulfur dioxide, the chemists will all know that sulfur dioxide and molecules that have a C double bond O group react to give what they're called addition products. They react to give sulfonates, which is this. So I'm going to talk about it. So there's sulfur dioxide. That's what's coming out of the mantle at a phthaleite quartz magnetite redox state. It dissolves in water and gives bisulfite. By the way, they put that on your grapes before they ship it to try to keep the oxidation down so that it preserves the grapes for market. That's why you wash your grapes, by the way, before you eat them, unless you're like me, which doesn't care whether I get some bisulfite or not. There's a carbonyl group, C double bond O. There's another one, C double bond O. This is on the 1 carbon species formaldehyde. This is on the 2 carbon species glycolaldehyde. Those 2 yellow electrons, which are represented by 2 dots on sulfur, form a new bond between the sulfur and the carbon, and it gives you this molecule here. This molecule is the addition product with sulfonate of formaldehyde. You'll notice it does not have any C double bond O group. This is the 2 carbon addition product. And the important thing about these is that, first place, they're stable because they lack a C double bond O. They're actually quite stable, even to ultraviolet light, not so much to cosmic rays, but never mind. The sulfonates are stable, and so they are dissolving in water, and they're going to rain out of the solution. And so you're going to get, I got the numbers right, you cannot not have had on a square meter, right, 10 to the 23rd molecules of this sulfonate raining out. I would like the geologist to tell me a better number for the flux of SO2 from the Hadean mantle. We actually, if you look at the modern flux of SO2 from the Hadean mantle, it's actually quite corresponding to the amount of formaldehyde they're generating. It's like you almost get a molecule of sulfur dioxide for every molecule of formaldehyde made. But of course, in the Hadean, there could be more, right? But then Jim Casting tells me because a lot of the sulfur dioxide that's coming out of the current volcanism is due to subduction of some kind, and it could have been less, but I need a better number from those of you. How many of you said you were geologists? There were a lot of you, so you can give me a better number at the end of the lecture. So that's cool. Now I want to talk to you, all of the people who are not organic chemists, a word about this carbonyl compound, because this C double bond O, a carbon doubly bonded to oxygen. This group is really, 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 really very, very important to all of the discussion today. So if a carbon of a C double bond O is attached to another carbon, C, that has a hydrogen attached to it, it cannot not react. How are we doing? So there you go. Formaldehyde, by the way, doesn't have anything worth, I mean, doesn't have anything attached to it. So the formaldehyde, which is this molecule here, right, has a carbon double bonded oxygen for sure, but it's not attached to another carbon. So in fact, the only kinds of reactions that this can do is, well, there's a whole series of them. And Jim pointed out that his review article had one that I was not familiar with before, even after I read his article. So there you go. But the bottom line is that there's a case where glycolaldehyde has this carbon, there you go, with a C double bond O attached to another carbon, which is attached to a hydrogen. And when that happens, you can have a process called enolization, which gives you a double bond, not between the carbon and the oxygen, but between the carbon and the adjacent carbon. And that causes these carbons to be able to react, including with another molecule of formaldehyde. 2 carbons plus a 1 carbon formaldehyde gives you a 3 carbon, which the name is not stibnite, not pyrite, not monazite, but glyceraldehyde. Okay, so we've added a 1 carbon to a 2 carbon to get a 3 carbon, and we're able to do that because you have a C double bond O carbon attached to another carbon, which is attached to a hydrogen. And so there you go. I'm going to ask you all the tests we're going afterwards to look for those. Whenever you look for those and you see those are important things to look for. And now there's a problem. It turns out that if you then go on and add the 1 carbon formaldehyde to the 2 carbon glycolaldehyde, you get a 3 carbon species, and you'll discover if you look closely that this also has a C double bond O attached to a carbon, which is attached to a hydrogen. And what that means is that it cannot not react. Okay, and it will react further and go through this process. And if you do this repeatedly, you get plots that look like this. Now, you got to look carefully here because I got these molecules all arranged. So the first row up here has 2 carbon and 1 carbon species and 3 carbon species here. There are 4 carbon species here. There are 5 carbon species here. There are 6 carbon species in rows. Every time there's a C double bond O adjacent to a carbon with its hydrogen on it, I get you an arrow that goes down. Eventually, we get compounds that don't have that, and they fission to go up. And this is a complexity that is, on one hand, good. You got a lot of molecules. But on the other hand, you don't want a lot of molecules because this eventually becomes tar or asphalt. But let me talk about the good part here, because it turns out that glycolaldehyde catalyzes the additions of formaldehyde. And the reason for this is because of this little cycle that I have illustrated here in magenta. So glycolaldehyde, 2 carbons, adds 1 carbon to give a 3 carbon species. This undergoes these reactions. It becomes a 4 carbon species and goes to a 5 carbon species. And this 5 carbon species, if you look closely, has a C double bond O, but the carbon that's adjacent to it is not attached to a hydrogen. So this cannot not react. It falls back apart. And when it falls apart, it follows these 2 big magenta arrows going up, and it makes another C2 species, another C3 species, and these kind of cycles. Now, I'm going to put that up a little bit bigger so you can see it. Okay, since you can't see it in the back from the previous slide. So there's your C2 species. You'll notice the C double bond O adjacent to a carbon with a hydrogen. So this can react, and it can add a formaldehyde to become C3. This has a C double bond O and a carbon with an adjacent hydrogen. So this can react, and that can add to form this carbon here and this species here. This has a, this has, of course, a C double bond O adjacent to actually 2 carbons that have a CH on them, and they can go here. And when you get to this species, you'll notice it does have a C double bond O, but that adjacent carbon does not have a hydrogen. So it can't react further. It falls apart, it fragments. And when it fragments, this is a C5 species. 1, 2, 3, 4, 5 carbons in this molecule. When it falls apart, it gives you a 2 carbon species and a 3 carbon species. And Hyojun Kim and I in my lab with carbon-13 isotopes worked through all these chemical things. And you can go see a paper in 2011, which is probably the most boring paper in the literature that year, which goes through each of these steps and measures rates for them and so on and so forth. Now, so let me just have a closer look at this molecule. There's their C5 carbon species. By the way, this is C5H10O5. Strangely enough, that's the same as the molecular formula of ribose. And strangely, when these two fall apart, they'll give you the 3 carbon species and the 2 carbon species, which I've color coded so you can see where the atoms are coming from. This guy has a C double bond O with an adjacent carbon with a hydrogen, magenta, and these actually can condense to form ribose. All right, so there you go. So you cannot not have this chemistry going on early Earth. Remember, you have about 1/6 of a mole of this carbon per square meter falling out of the sky per year. And so that's great. Now, however, this is the bad side. Unlimited reactions are not good, right? The fact that I make ribose is fine, but I'd love to have ribose if I'm worried about RNA. But ribose has a C double bond O attached to a carbon, which is attached to a hydrogen. And I can get you all to say in unity, that means that it cannot not react. All right. And so it doesn't react, and it analyzes and it forms alkyl reactions and it generates tar. You saw, Jim, you had this caramelization, didn't you, on your slide? So there you go. Some nice caramel, very tasty, but not good because this becomes extremely complicated. And although we do have people, and I really encourage this kind of work to try to see whether complexity can give you life. This is not what Stanley Miller concluded. Stanley Miller concluded after measuring the rate at which ribose reacts, concluded that stability considerations preclude ribose and other carbohydrates as prebiotic reagents. Ribose and other sugars were not components of the first genetic material. Now, for those of you who believe the standard model for the origin of life because you were taught it in school, there you got a problem, because if you don't have ribose, you don't have R. If you don't have R, you don't have RNA. Okay, that's a problem. Okay, so now there's the enormity of the problem. I've just shown it to you. I can point out compounds here. So I mean, you go through every one of them. There's a nice blue compound, has a C double bond O. You'll notice the 2 hydrocarbons next to it. Neither of them actually have a hydrogen on it. That's actually a relatively stable molecule as things go. For the people in the audience who are chemists, that actually suffers Cannizzaro reduction from formaldehyde. That's actually what the fate of that molecule. There's a whole industry in Japan trying to make food out of formaldehyde, which is based on that as an endpoint of this process. But otherwise, I've gone, you get to the end of these boundaries, okay, you can still see, for example, here's a compound which has a C double bond O with a hydrogen on the carbon adjacent to it. And that means there's a whole more reactions that are going down off this piece of paper, and it's a mess. And that's what gives you the color eventually. So this is why sulfur dioxide addition is so important in this process, right? So formaldehyde, H2CH2O, and glycolaldehyde give you these organic mineral reservoirs. These guys have no C double bond O in them, so these are actually quite stable, and they will fall to earth and accumulate. Now, there is, of course, a reaction, the reverse reaction. These can't do anything. These actually, you can heat these, you can do anything you want. They do one thing, of course, that is go in the reverse reaction in the direction in which they made them. So they can eject sulfur dioxide and go back to give these species which have C double bond O's and CHs adjacent to them. And that's, of course, becomes important to us. But of course, that means that the glyceraldehyde sulfonate, that is this nice guy, the 3 carbon species, and the glycolaldehyde sulfonate cannot not bleed C double bond O back to the aquifer. But your problem is, but then you just get tar again, just to get it slower. So I know that seems to me to be not a terrible progress. So now let us now introduce borate. So this is why I'm in great love with boron. We call it green because it has a nice flame green color, right? Boron loves to coordinate molecules which have 2 OH groups, which I've also labeled here in green, adjacent to each other. So there's one of them and there's one of them. Borate will form this complex. For those of you who have ever made slime in your school child days, you take starch, you put borax in, you mix it around, it makes a nice gooey globby stuff. And that's the boron cross-linking the starch molecules by forming a complex with the 2 adjacent OHs on glucose, which are, of course, the building blocks of starch. So this is a very well-known reaction, it's very well studied, and it's got all sorts of things. But the point that you should notice that if you have been studying all those slides earlier, you will notice that there are adjacent OH groups everywhere, okay? Okay, and let's pick your favorite compound. Okay, so here's a compound over here. This one, right? There's an OH on that carbon, there's an adjacent OH on that carbon, there's a CH2 with an adjacent OH on that carbon, there's an adjacent OH on that carbon, there's an adjacent OH on that carbon. Boron, borate is going to coordinate it. Okay, the only question is which of those complexes is more stable, and you can go throughout this entire, but as borate dives in and sees nothing but things that it can coordinate to, and it does, it cannot not coordinate it to them. Okay, and so the minute you start talking about boron coordinating the things, all of a sudden you discover that it controls the reactivity of that mess. In particular, right, there is a 4-carbon species, which I have actually on the previous slide, but I didn't point out. This comes from the addition of the 3-carbon species, glycolaldehyde, to a 1-carbon species, formaldehyde. 4-carbon species, 2 adjacent OHs. What happens if borate gets it? It coordinates. Okay. Now, the minute it coordinates, the borate complex, by the way, has a negative charge on it, and it controls what this molecule does. Now, this has a C double bond O. There's a hydrogen on the carbon adjacent to it, but because this whole thing is coordinated to borate on this side, that hydrogen no longer comes off. On the other hand, on the other side of the C double bond O, there's another carbon with a CH on it, but there's no borate coordinated over here. So that is where the hydrogen comes off. And so that determines which direction this molecule, which would normally react on both the right side and the left side, because on the right there's a CH and on the left there's a CH, but here it only reacts on the left. And then even better, what happens is the boron coordinates here, it guides the formaldehyde to the more hindered center, and that's actually where you get this species that I showed you on the previous slide, C85H10O5. It's the same formula as ribose, and therefore this branch, this species is actually quite special, it's quite nice, it cannot not form a cyclic form that binds borate very tightly, and it must accumulate in the aquifer. And we put up this paper a couple of years ago with this whole group that was meeting in Atlanta on under the auspices of the Templeton Foundation grant, which put this all together, so you can go see it in detail. So there's some more of the species. There is your 5-carbon species. I won't go to great lengths to discuss why this happens, but this actually forms a cyclic species which coordinates borate that does not have a C double bond O group. However, if it's open in this form, it can fragment to give these 2 pieces, which I had red and blue on the previous slide. And these can recombine to give ribose, which is a very stable borate former as well. Okay. So that's kind of cool, right? So what we have is that borate is keeping things within this box by coordinating to OH groups of the C double bond O compounds, determining how they react, and preventing this huge mass of tar forming reactions that would go by going and going and going. And that's, of course, a big thing for us. So now we can add to what chemistry could not have happened is if you have these sulfonate derivatives, and remember, you have about 1/6 of a mole per square meter per year of the first one coming out, 1 part per million of the second, right? You could not also not have this branch pentose with a cyclic borate as an organic mineral, as well as ribose, as well as, by the way, other C5 species, which I'll mention. Okay, now there's a problem here. I've added something to your geological model that I did not tell you before. Told you before we had to have a phthalate quartz magnetite redox potential and all the rest of it, but now we also have to have borate, and we have to have constrained subaerial aquifers, right? So we had to have sort of what we would call dry land. Now, I'm agnostic whether we have lakes, like you heard earlier today, or hydrothermal springs, like you heard from Martin yesterday. But the bottom line, you do have to have contact to the air, which is what's making the 1/6 of a mole of formaldehyde sulfonate every year. And of course, you cannot have that stuff diluted into a global ocean and expect it to be terribly productive to you. So so Bob Hazen gave us a lot of grief on this. Actually, he's such a nice man. I have a hard time arguing with him, but he and Ed Grew in Maine said that we couldn't have borate. And he is, of course, has a great series of papers talking about when minerals become available in the natural history of the planet. And so boron was the argument, but boron is not very abundant, right? Boron is not made very effectively in stellar synthesis because boron itself as an element has a very high cross section for neutrons. So it goes on to other things. And so most boron is made is what's by a process called spallation. And so the amount that you have is not very high. And so what Bob was saying was that you needed a lot of plate tectonics before you could churn the planet to have enough fractionation processes to concentrate borate. And Bob did a pretty good job arguing this. Our argument in rebuttal is, of course, that borate is such a bad mineral forcing species that it gets concentrated in the residual melts of lava. And so what ends up happening is you'll see them coming to the surface of the Sierra Nevadas or the surface of the Allen Hills range. And so what comes out of the early weathering of these rocks is borox, actually, and that's why you get Death Valley has a 20 mule team mining borax there, and that's how Ronald Reagan got his start in politics. But the bottom line is that, so Bob at this point, however, finally conceded because on Mars, Patrick Gassa has a wonderful paper, 25 to 40 millimolar Mars, borate on Mars, which we can get. And of course, Mars does not have the plate tectonic history that it, so it looks like the borate is certainly concentrated in the residual melts of the lithosphere, but also in the aquasphere. So but we still don't know whether we have any dry land on Earth 4.3 billion years ago. This is actually from Jun Karanaga, a great plot. Like all geologists, he writes the time scale backwards. So this is today, and this is the ancient Earth. And these are all the various statements about how much crust there was on at the time before present as a function or ratio of the amount of crust we have today. You got to remember the amount of crust is not the amount of dry land, but never mind. And of course, we're going to talk a little bit later about impacts where meteorites would have come in and reduced the oceans to some extent. That would have created more dry land. But this isn't really our first things that did not happen. Okay, so we don't really know that you have a lot of dry land exposed to so I mean, Steve Moishes has given me roughly 1 Australia of dry land, maybe broken up pieces. So that's and these are based on isotope. I know oxygen, all sorts of oxygen isotope ratios, and people are trying to do calculations. But I could use from the geologist before the end of the day a better number. So well, he's a better statement about which of these curves is more likely. So there you go. So now you have one piece of a discontinuous synthesis model for making RNA, and a lot of it could not have happened, at least if you give me borate in dry land. The borate is being used with the sulfur dioxide to manage this tar paradox, and you're getting to these branch species which can rearrange to ribose, which then form very stable borate complexes. And so there's the R in RNA, and that's not so bad. And there's also further evidence that this actually is natural. So my buddy Yoshi Furukawa published a paper a couple years ago reporting ribose in meteorites. And you heard a lot about meteorites earlier today. I'm not saying that the ribose in the RNA that sparked life came from meteorites. But what the meteoritic presence of ribose suggests is that these kinds of processes can occur naturally. If they on the meteoritic body, if they can occur in the meteoritic origin body naturally, then it can occur on Earth naturally. At least that's the argument. The logic is a little dodgy there, but there you go. So, but it's quite clear that borate's on the surface of Mars. There's carbon dioxide on the surface, above the surface of Mars. There's water, not a lot of it, but certainly enough to make this chemistry occur. So I know I wouldn't be surprised if borate stabilized ribose is on Mars today, right? And again, because it doesn't have any C double bond O groups, it does not have much UV absorbance. It's fairly stable. Of course, the cosmic rays that do also make it through the thin atmosphere will pulverize it. But of course, ribose is only one building block of RNA. So here we are. And you got to keep in mind, our model for the Hadean is too placid. The Hadean also has impacts. There you go. A nice little dinosaur extinction graphic. And we know that the Hadean has about 10 to the 26 grams of impactors. And the way we know that, for those of you who are not geologists, is because there's a whole bunch of ideas that Goldschmidt put forward about how the various elements decide whether they're going to go with the iron and sink to the core once they arrive on Earth, and which ones are going to remain in the rocks. the ones that sink to the core and the red, the ones that remain in the rocks are with the sort of the orange, and the ones that remain in the rocks with, as long as there's sulfur around, in yellow. Of course, the ones that are in the atmosphere are in blue. And one of the things you'll notice is that all the good stuff like gold and silver goes down with the iron. And so, well, the gold certainly does, the platinum. But there is, of course, in our crust a veneer of gold and platinum that are created after the core closed. And the amounts of that requires about that many grams of impactors and enstatites, okay, with an N. And the lower lunar veneer has been argued that means that you have fewer impactors bringing most of it. So it's not coming all in by micrometeorites, but there's a number of larger impacts so that you can have the statistics of small numbers get you the veneer that you have on the Earth without having the veneer on the moon. The problem with that is that the number of the veneer on the moon has large error bars associated with it. So, okay, so you have various impactors that can come in, and the question is, there's a graph that we picked out of Steve's stuff. But you know, so now the question is, what does a 10 to the 25 gram, say 10% impactor not do to the Hadean atmosphere? Well, that's lots of things, right? It resets mantle clocks. It certainly killed any life that was pre-existing for that size. It had its own iron core. It's big enough to have its own iron core, which could shatter. And if it does that, it would reduce things. It's insufficient to reduce the mantle, but it did certainly reduce the atmosphere from the iron and the nickel metal that are in the shattered core. And the minute you reduce the atmosphere, all of a sudden you don't have carbon as CO2, you have it carbon as methane, you have nitrogen no longer as N2, you have it as NH3, you have H2S, you have all these various things. But you also have these compounds which prebiotic chemists from the 1960s love, like hydrogen cyanide, cyanoacetylene, HNCNH cyanamide. These are all not available in the standard redox neutral atmosphere that I started this talk with, but they're all available here. So a new kind of chemistry occurs transiently before the atmosphere returns to its neutral state. So I gave this talk about 2018 in Caltech, and Kevin Zomley was in the audience, and he very nicely then whipped up these plots. And then this has actually been published with Dave Catling and a few of their students. So you're looking at, this is a Vesta size impactor. It's considerably smaller. So you have for about 500,000 years, a reducing atmosphere, which has some methane. It has, that's the green curve. It has hydrogen cyanide, which then goes away. The hydrogen is, of course, made initially, but then, of course, it's distilling into space, which is why this is returning to a relatively redox neutral atmosphere. And the CO and CO2s are bouncing around. So there you go. So you have 500,000 years after a Vesta size impactor to drop not only glycolaldehyde and formaldehyde in sulfate forms onto the surface, but you have 500,000 years to also drop juicy stuff like these nucleobases. Now, I'm not going to go through this. Kid who died there, Maruyama, have excellent reviews. This is classical 1960s prebiotic chemistry. So some of these syntheses are actually quite efficient. So again, because of these compounds in the immediately post-impact reducing and atmosphere cannot not be made, you are getting all these molecules available as reduced primary precursors made in post-impact atmospheres for the bases of RNA. Okay, so we have another piece of the so-called discontinuous synthesis model. We have the pieces coming out of ribose, which of course is coming from formaldehyde at the level of 1/6 of a mole per square meter per year, and glycolaldehyde at 1 part per million, with borate constrained in its formation of these 5-carbon sugars, which pretty much are the endpoints of that maturation. And we have the bases, okay? So now what? Well, one of the things that's amusing is when you're sitting there worried about two processes of what's going on the Earth's surface, you have volcanism, which of course is coming from below, and you have impact. And what they're doing is generating together basically lava. Of course, if it's a series size impact, the entire planet's surface is a molten lava. If it's Vesta, it's local. In fact, there could be parts of the Earth where life would have survived a Vesta-sized impact in a refuge of some kind. But the point is that this entire surface is covered with basalt, basaltic glass. For those of you who are familiar with basaltic glass and its diagenesis with water, it goes and forms zeolites, mordanite, all the way up to, actually I meant prehnite, I guess is one of them. I saw that yesterday in one of the talks. So the question is, what happens? And this is a goof. I got to say that I didn't think that this was going to work, but the question was, suppose we had nucleoside triphosphates and we incubated them with basaltic glass, what happens? Well, this is Elisa Biondi who did the work, and you're actually looking at experiments with radioactive material, where you're looking at a variety of different kinds of glass. Okay, so we got these from the US Geological Survey. There's basaltic glass, there's diabasic glass, there's nephelinic glass, there's a bunch of these things. They don't all work all that equally well, but the basaltic glass is making from precursor RNAs. This is a gel electrophoresis experiment where the building blocks are running down at the bottom, so they are radioactively labeled nucleoside triphosphates. And over time, you're accumulating high molecular weight RNA between 100 and 200 nucleotides on average. And that's again, the statement here is that it's not the same for all glasses, but okay, great. I mean, this is what we're done, right? We've got RNA molecules that are, well, there's a couple of issues here. We'll put that on as a third piece of the discontinuous model. There are a couple of questions you can ask, like, what kind of glass works? Now, I put this diagram up without having a clue as to what significance it is to a geologist. I mean, you're looking at here on SiO2 on this axis and Na2O and K2O on the vertical axis. And I put the dots on what we tried glasses. I have no idea what that means by the microscopic structure of the glasses or what they might catalyze or not catalyze. But the bottom line is that the three ones in the middle work pretty well. The ones on the outside don't work so well. So the andesitic glass does not work very well. The nephelinite glass does not work very well. But the basaltic glasses, these things. And for the life of me, I can't tell you what the difference is between diabasic glass and basaltic glass, because it seems to me that the difference between diabase and basalt is just grain size. So I don't understand how that makes a difference when you make a glass out of it. But somebody in the audience is going to correct me in the question. And, oh, I see someone taking me up on that right away. So there you go. But these work. The ones outside don't as well. The silica glass, pure silica, doesn't work at all. And I don't know why. But never mind, we can attack this as irrelevant, okay? So the first question is, all of these glasses are coming from the US Geological Survey, and to make it matters worse, that since COVID, they have stopped shipping these glasses. So we have got a big muffle up and we're collecting rocks. But we've gotten some, we paid $400 with the Iceland to get some of this tholeite, which maybe you guys know what that is, right? But it's, okay, some kind of vessel. Well, I've gone to Mindat and see that there's actually a name here. And this also, so natural stuff from Iceland also makes RNA. And this is from what we got from Bettina. So there's the RNA being made. It also turns out if I leave the diabase glass and expose it to oxygen and something, it goes away. And I have no idea why that is. But the bottom line is that we can get this out of natural glass as well as synthetic glass from the Geological Survey. And as far as I can tell, all that the Geological Survey does is goes out to Table Mountain outside of Golden, Colorado, and picks up some rocks off the ground and melts them. But I can't really get them to tell me what the provenance of this is. But never mind. One of the other issues which you might not like is goes back to the chemistry. Now, RNA has this structure, which I will point out to people, where I have in your RNA is natural what's called a 3' to 5' linker. That's where the OH here forms a bond to the phosphate here, which forms a bond to the oxygen there. And that's how that link is together. There is another possibility because there are two OHs here where you can have the 2' O, this oxygen, not that oxygen, form the bond to the phosphate and go to form the bond to the next link. This is natural, this is unnatural, this is degraded by enzymes, this is not. What you're looking at here is for a series of these RNA molecules made with different compositions, the ribonuclease enzymatic degradation of the RNA molecules that are made on basaltic glass. And the fact that most of these links are degraded suggests that most of these links are 3', 5'.
and we cannot actually detect really any of the fragment that comes from 2' to 5', which means we think that most, but certainly a large amount of the linkages are the natural linkage, which means that the basaltic polymerization is making sort of natural looking like RNA. But so there you go. There's another piece of the, but the problem is that the good parts, right? The ribose, which of course Stanley Miller would not let us have, but we now have with borate. And of course this, which is great stuff from the 1960s. And then this stuff, which Elisa Biondi, they're disconnected. We don't have anything in the middle. So the question was, of course, is relatively simple, okay? Where these things come from. And there's the complete proposed model for a more continuous making of oligomeric RNA from precursors like hydrogen cyanide and formaldehyde. But it repeatedly uses basalt and basaltic glass and borate glass. And we're going to now throw another thing which we don't understand here, is that phosphate in basaltic glass is thought to be in condensed form with high energy POP, phosphorus, oxygen, phosphorus units. And that's actually something that was proposed by Niels Holm in Sweden. He has a whole series of papers on this. But never mind, there you go. So now where do the triphosphates come from? Now I recommend to all of you that you go back and just page through these geological reports. This is how you put yourself to sleep at night. And I'm reading through these things and I get to the one on Lüneburgite. Now I don't even know where Lüneburg is. It's in Germany, actually, in Saxony. But then I read through this whole thing, and then I notice its associations with with gypsum. And that strikes me as odd, because for those of you who are interested in the phosphorus origins of life, you know that calcium is an enemy. Calcium precipitates phosphate as apatite, and that apatite is generally regarded as non-accessible. Now, Nick Hudd has a very eutectic approach to getting phosphate out of apatite, and I just talked to one of the students here yesterday. I think he's going to talk later, but there are other ways of doing it. But this illustrates the problem. If I take calcium and magnesium and sulfate and phosphate, I get apatite and epsonite. What if I put, guess which element? Martin. Exactly. Borate into this mixture. The partition is different. Calcium and sulfate go to give gypsum, and phosphate, borate, and magnesium go to give Lüneburgite. And you can do this in the lab. I mean, you just mix them. And there you are. You can see the crystals of gypsum, and you can see the crystals of Lüneburgite, and that's quite remarkable. So Lüneburgite is a magnesium borophosphate. And so if I dump a nucleoside on it, the adjacent OHs, which you have learned now are important because the adjacent OH groups, there they are, grab borate, there you go, that corrodes the mineral, and the mineral, as it's corroded, generates phosphate. So if you heat it up in urea, you get diphosphate out of the nucleoside. Where boron, because it's grabbing the two OH groups here at the bottom, protects those, it blocks those, it keeps the phosphorus from going on the bottom. Remarkable. And I thought that was pretty good, but then we did something else. This molecule you'll see is cyclic triphosphate. It's actually something you'll see Ram Krishnamurthy. There's a lot of people who are interested in this molecule. That's one you'll see later. It turns out that if you take the nickel from the meteorite and the core after it's shattered and been oxidized, and you put this in with the borate protecting these two agents, you make the triphosphates. It's a very high reaction. It's something we've actually considered manufacturing triphosphates for sale and commerce just by taking the cyclic triphosphate, a little bit of boron to protect the two adjacent OH groups, and putting those on. So they've got all kinds of ways, and Sidney Becker, who works with Tom Carell, reproduced this. We had a lot of people making it this way. So that's a piece of the puzzle at the bottom. But then you can still ask, well, where do the ribonucleosides come from? That is, these species that are going to get made into triphosphates. Well, it turns out that there is a very interesting reaction, which is going from ribose cyclic phosphate. But that's actually ribose sitting here on the left, and the cyclic phosphate is this thing here. And if you mix it with adenine coming out of the post-impact reducing atmosphere, and you put it in calcium and you dry it out to 100 degrees centigrade, you make adenosine phosphate, actually. Guanosine, not so good. Cytidine, a little bit better. U, not so good at all, but of course the C can be converted to U. And so you can actually just make all of these nucleosides just by mixing the stuff coming from the atmosphere with the ribocyclic phosphate. Okay, so there's a piece which ties now the nucleus bases coming from a reduced primary precursors from a post-impact atmosphere. How long it has to make those depends on how big the impactor was. Going all the way to triphosphates, going all the way to polyribonucleic acids. But you get to ask the next question, right? Where does the ribocyclic phosphate come from? Well, this is actually Krishnamurthy's chemistry. This is from 23, a quarter century ago, right? Where he pointed out if you take this cyclic phosphate, which again is maybe in volcanic or impact glass, and you have it from ammonia, which of course is coming out of the post-impact atmosphere, it makes these molecules, including this diamidophosphate. And what's nice is that ribose with diamidophosphate goes bang over to ribocyclic phosphate. And so in case you haven't noticed, we have now completed the cycle. There are no more steps that we don't have something working for. But now you got a job, and this is why we train students, right? Once you come up with your favorite model, what you're supposed to do is attack it, right? That's the correct thing to do, because if you don't, I mean, Albert's going to do it or somebody's going to do it. And then, you want to have the attack already under control before. Well, actually, Albert has been very nice to us, but John Sutherland will go after us like nothing else. Okay, so great. So the bottom line is that sometimes something is here is not privileged, okay? There are things on this thing, which I've already mentioned. Of course, the dry land, it's open for question. But some of the steps might be hopelessly incompatible. Let me just put one of them onto you here. So I have, let's follow from the center of this chart. There is the borate ribose complex, which I love because it's stable, accumulates, organic mineral. I got to go to this, but would you not expect borate to inhibit going from the borate complex to here? Let me just put a little bit more detail up here. There's actually a lot of chemistry going on step one, actually step two in this direction. Let me just show it to you. So there's the borate ribose. It's got to get rid of the borate to get ribose. But ribose is in this so-called ring-closed cyclic form. It's actually the major form. It has no C double bond O. It's got to open. And then once it's open, it has to react with Krishnamurthy's diamidophosphate to give you this intermediate. Then this intermediate has to do these little gyrations to go give a midocyclic phosphate, which I've drawn here. And then that's got to go to give another intermediate. And that's got to go to give another intermediate. And only then do you get ribocyclic phosphate. And you can say, if I've got all this borate around and I want it because I want to keep the ribose stable, doesn't borate shut this whole process down? So this, we thought this was where the discontinuous synthesis model was going to fail for sure. Borate surely holds the ribose in a ring-closed form, unable to react with Krishnamurthy's diamidophosphate. So, as I've already mentioned, Yoshi Furukawa, he sent his student Yuta Hirakawa to my lab the last October, and we just tried to put these two steps together. So what we're going to try to do is we're going to try to start with ribose borate and try to get to Krishnamurthy's cyclic phosphate without any special ways of getting rid of the borate to freeze up. And the amazing and surprise was that you just showed that this whole damn thing is cleaned up by the presence of borate, because borate is actually catalyzing the conversion of this intermediate to that intermediate. So borate does not inhibit this, but borate actually wings this stuff along and actually makes the yield of the ribocyclic phosphate much higher. And you can actually see on the chromatogram I just showed you, which I'll go back to in a minute, this ACP peak, right, which is present without borate, is gone with borate. So it doesn't accumulate as an intermediate. So there's the diaminophosphate, that's Krishnamurthy's starting material. There's inorganic phosphate, which we use to standardize the NMR, and you're getting 100% of ribocyclic phosphate if borate is present, but not if it's not present. So there you go. So that is what's making this model clear. And this is, of course, actually, and Hyojun Kim, I should mention also, of course, was involved in all this work. So then, of course, you just say, well, what the hell? I mean, we don't have any reason why calcium should interfere with this step, or why urea, which we have in here, should interfere with this step. so Utah is able to go all the way from ribose borate complex all the way to adenosine phosphate in one pot just by mixing these things, heating them up to evaporating off at 90 degrees centigrade. Okay, so it's a continuous process from ribose borate all the way over to adenosine monophosphate. Sometimes you're lucky. Okay, but there's still a lot to remain to attack, and let me just reel these off so you get a chance, because I'm about to finish. Homochirality. All these molecules have to have the same chirality. We don't know how to do it. By the way, just if you follow it carefully, for those of you who are good in organic chemistry, you'll see that there's one stereogenic chiral center in this entire system, starting at the left, and that's this carbon here. And once you figure out what the chirality is here, that chirality propagates throughout the entire cycle. You never need to worry about it again. So we were hoping that the stereochemistry, which is sealed at glyceraldehyde, would crystallize, and we would get chiral resolution. But these molecules are very, very soluble in water, and so we've never gotten any of them to crystallize. There you go. But maybe some other salt, maybe the barium salt. Okay, the second thing is I mentioned this branch pentose, and I'll just mention it again. It's a very stable intermediate. This is the one that has C5H10O5, but is not ribose, which has to fall apart and become two fragments that go back together to give ribose. They can also give this C5H10O5 compound ribulose. This borate complex is so stable, it takes years to get that reaction to occur. But okay, now you can argue that's good, you can argue that's bad. Obviously it's good because it means that this molecule will build up as an organic reservoir. But you know, it takes a long time to get the ribose borate out of that. Again, we don't know that we don't have a substantial amount of the 2' O' linkage in that. And these are all things. But we really do have geological problems that remain. And I'll just tell you them again. I've mentioned them. I don't really know what the flux of SO2 is in the Hadean. We would really like to have a number on that. We don't know what the flux of solar energy is in the Hadean. There's still a lot of disagreement on that. We don't know how we mobilize these condensed phosphates from basaltic glass. Okay, there's some springs, hot springs in Kamchatka where they've got a lot of pyrophosphate, a lot of the stuff. So maybe that's the answer can be found there. I'm not familiar enough with that geological terrain. And of course, we still don't know that the Hadean has constrained aquifers accessing the atmosphere because you have to get all this stuff, including the nucleobases that were in blue, as well as the sulfonated stabilized sugars coming from the atmosphere. Okay, so there you go. That's the standard model for the origin of life. We need a scheme to make 100 to 200 nucleotide RNA biologically. You've seen it. But okay, are we really done when we've made it? Well, you know, great. I mean, Darwinism maybe began with RNA able to catalyze the template-directed synthesis of RNA, but the fact is that RNA turned out to be a pretty bad catalyst. We have many examples, but we are even more examples of RNA molecules that catalyze the degradation of RNA. So if I make, you know, a random pool of RNA sequences, the number of molecules that degrade RNA is probably 10,000 to 1 over the number of molecules that make RNA. So we've got a problem. We need compartmentalization. You heard some about that yesterday. Of course, our solution to this is maybe the RNA had more building blocks, but that's going to get me into the synthetic biology part of this talk, and that's a talk for another day. So let me stop. Thank you for your attention and be happy to answer any questions you might have.
Thanks very much, Steve. That was a fantastic overview. Are there any questions? Let's start here.
Sorry, a big question. Is this chemistry happening in solution phase or in the gas phase, or can it happen in both?
Okay, so the sulfur dioxide plus it's gas, and of course formaldehyde is nominally a gas, but they both partition quickly into aerosol water droplets, and so that's occurring in dispersed aerosol droplets. So today, right, there's an industrial pollution which is formaldehyde, and there's of course sulfur dioxide coming from industrial pollution, and we're forming these compounds in the earth in aerosol droplets in clouds today, which is where the most of that material partitions. Now, when it rains to the surface, it's occurring in aqueous buffer. Oh, well, it's aqueous solution, rock buffered in some sense. But what has to not happen is it has to not be dispersed into a global ocean, because I know the concentrations of the borate is a useful species at a concentration of say 25 to 50 millimolar. It can't be, I mean, if I just do the mass balance of how much boron I have on Earth, I just can't put it into an ocean. So then most of these things are, so that one of the, we are looking at reactions that are slow at room temperature, but where you'll see frequently we evaporate these molecules to dryness at 90 degrees, something like that. And you'll also see frequently, and this is all post-impact stuff, you'll see urea in lots of these things. And so urea, of course, is coming from HNCNH, the cyanamide, or H, that's not how it's often written, but the bottom line is that hydrolyzes, that formation of that molecule is gas phase. And the maybe associated with particulate catalysis, that's something. And then, of course, the hydrolysis of that is occurring all the time. Like it's hard not to have that urea form from that molecule. And so almost all of that is occurring in aqueous constrained aquifers up to maybe 100 degrees.
Andy? So, coming at that from a geologist, it seems to me that boron has been a limiting reactor. That probably limits the number of places where this can work. Johnny was just saying relative confidence in the question is when they emerge to probably a place where have you thought about that yet?
Yeah, so that is the essence of Bob Hazen's and Ed Gru's argument. They say you cannot have any of this borate that you want unless you have continental crust formation. That requires of churning, if I may be crude, which is leading to fractionation. I mean, the Earth is badly mixed to begin with, right? I mean, someone didn't get up there and do a good job of mixing it after the core closed and all the rest of it. But the bottom line is that Gru said there is no continental crust and there is no mixing, and therefore there is no concentration to the 25 to 50 millimole that you need before plate tectonics. And so you can't have it at 4.3 plus or minus 0.05 billion years, which is why that number is coming from our assessment of the size distribution of impacts, right? So that's where that number comes from. If it's older, it's the moon forming event, we're not going to be doing any of this. But so the answer, what basically shut Bob and Ed up was the finding of that amounts of borate in the surface of Mars. Now, I don't know. Well, you're not talking to anybody who knows anything here, right? So how the hell does Mars get available to a rover where it's wandering around? They finally get around to doing the elemental analysis for boron. By the way, that was not a capability they had on the earlier rovers. How did the boron get there? Now, I mean, that's a question to you.
So it's curiosity that those sediments are probably about sediments.
So they're concentrated in the aquasphere, and that's the hydrosphere, whatever we call it. No. Okay, so no, I mean, I'm again, so what you're saying is that, yes, if I'm concentrating in the hydrosphere, then it's got to be at the bottom Death Valley, right? It's not on the slopes leading to Death Valley in particular. It's all been washed away. But yeah, so that would mean that you have local areas. It's not the whole planet that's active.
Yeah, we can talk about that. Joe.
I just had a quick look during your talk at the very briefly literature. It seems that Icelandic rocks do contain a fair bit of boron as well. So as well at this point, but it still could ultimately be related to earlier magnetic recycling. But in that setting, you still have so you don't need to confident.
Yeah, do you have any friends who are Iceland-based geologists who are? I didn't know that sentence had a second part to it. We paid $400 to go collect, and then I went into one of these lava tubes. And in the lava tubes, you have these stalactites coming off the surface, and so you ask the guide what they are, and they are apparently the residual melt. This is lava that is, and so I asked her, are those stalactites enriched in boron, right? Which of course she did not know the answer to. But I then have sent a lot of cold letters to various professors of geology all across Iceland, hoping that they'll find somebody who's done a boron analysis of who can tell me the elemental analysis of the stalactites as it differs from the bulk. Of course, I did not damage the park geological heritage by picking stalactites off the roof of the lava cave, but so all that we collected was in an area that was permitted based, it's a surface lava flow, so I don't have anything more than that. But of course, across that surface lava flow, there's going to be temperature gradients, which cause the stuff that's buried to, cool more slowly than the stuff on the surface. So maybe we would be able to answer that question. But yeah, so so I've asked everybody I know as a geologist, what's the best analog for early Hadean basalt? And they say Iceland's not a bad place.
But Iceland is something extra, which is that it becomes so thick that the base of it starts to remelt. Within 20 million years, and you get rhyolites and tonalites.
Okay, so it's
which are
fractional.
It fractionates, it remelts and concentrates again. So there's a internal secondary process that happens when there's water.
I say, are you Icelandic?
Sorry?
Are you Icelandic?
No, but I've been there twice. I've got a piece of Icelandic tonalite if you're interested.
Yeah, absolutely. Because I mean, the other place I have to go is somewhere in the South Pacific to that some hotspot volcano. And I was just in Hawaii and they wouldn't let me collect. So this is
so restricted.
Yeah.
Thank you for that wonderful talk. And this, I could be completely wrong, my thinking. But if there's a certain sequence for the nucleotides in RNA that are needed to for replication, is there any RNA sequence that cannot not be formed or more likely to be formed? And does that match?
I'm with you. I know exactly what you're saying. So there's 4 times 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 4. That is, there's 2 to the 200th 100 mers. And for those of you who can do the math, that's a large number. So the problem is, how is function distributed in that sequence space? In particular, how is catalytic function for the synthesis of RNA distributed in that sequence space? So Irene Chen and a number of other people have tried to explore that sequence space. And without going into great detail, the big conclusion is that sequence space is disappointing, meaning it has functionality that is sparsely distributed and it's in islands that are not easily evolved to from other islands in the sequence space. And so the answer to your question, we don't know. That's the short answer. But the major problem that we have with the RNA world right now is that it does not look like it's a terribly rich platform for catalysis. But of course, since that space is so large, and we haven't necessarily looked at it very comprehensively, we certainly not have looked at it systematically, we don't really know whether there are islands of sequence that would be useful.
Indra?
Thank you for that wonderful talk. It's like you're not from my part of the world, which is geology, definitely not part of from your world, but I'm very curious to know how did you pick boron 53? Okay, and have you tried any other element that might work similar to
Germanium. So I'm a chemist, and I have a periodic table on my lanyard, and I have a periodic table tie, and I have in my office, front office, a museum that rivals the Smithsonian, which includes a complete element collection of all pure elements, as well as the minerals from which they were derived, and in many cases, the minerals from which the elements were originally isolated. And if you're really good at this business, you get the mineral from which the element was originally isolated from the spot on Earth where that element. So never mind. So I am a nerd. Does that explain this to you? So if you, and the short answer to this question is the reason why we were directing this was because we were actually interested in doing what was called dynamic combinatorial chemistry to develop drugs. And we were interested in using boron as a way of coordinating fragments of pharmaceuticals, where when they're coordinated to boron, we have 2 pieces that are able to bind to your virus and therefore throttle it better than just having one of the 2 fragments. So that's what we were doing. But the bottom line was that other people have looked. So aluminate is something that also coordinates 2 OHs. Germanium does coordinate. Arsenic will do this. But now, and silicate will do this. But now your problem will be, let's talk about silicate. That's a great element, right? I mean, got a lot of that. But to get silicate into solution to the point where it coordinates 2 adjacent OHs requires that the pH go up. And the pH going up is what causes the C double bond O adjacent to a carbon with hydrogen to react. So that's every pH unit goes up, the reaction is 10 times faster. And so what happens is that to get silicate in to stabilize it, it loses the race. higher pH, yeah, more silicate, but higher pH, more instability. And this aluminate was a little bit better. There's a guy at Northwestern University who actually looked at this in some detail. Again, this is the same problem. Aluminate, you got germanium, you know, as a dynamic. I'm at first place. Germanium is not one of my top 10 elements on natural abundance in the crust, but it's dynamic. It goes on and off. And arsenate, by the way, arsenic DNA had the same problem. The arsenate esters they go on and off very fast and don't do anything. But yeah, you know, once you know all you're a geologist, so you're friends with all the elements in the periodic table, right? Except for technetium and promethium. But so you have the same sort of there's that kind of direction. There is no other element besides boron that's going to be able to do this.
Anyone else?
Yeah, I just have a question about geological chemistry. Maybe just clarify. So the branch pentose that you showed is a product of C3 addition to the C2.
No, it's the addition. So the branch pentose is actually the result of the addition of the C4 to formaldehyde. And that's why you don't get erythrose in any of these things. You don't really get any linear C4s. You only get erythrulose, which I'm now talking technology here, nomenclature. But yeah, so the reason why you get so what happens is, I mean, I did have that slide up, but it's a subtle point for anybody who is not in the chemistry community. But let me just see, there you are. So it turns out that when glyceraldehyde enolizes and it adds formaldehyde, you get erythrulose because the formaldehyde adds to the less hindered center of the C3 ene diol. So you have a CH2OH, a COH, double bond C, HOH, and the formaldehyde goes on to the third carbon. So the latest formaldehyde to arrive in this particular molecule is this guy here. There, this guy is the guy who's arrived last, and he's going on to the ene diol of the 3-carbon species where there's a double bond here between an OH and an OH, and that's the less hindered center, so that's where it goes. And borate is not coordinating very effectively to the ene diolate of the 3-carbon sugar because it does not have adjacent OH groups. You with me?
Yeah.
So that goes here, and then that boron coordinates here, and that is what pulls on that oxygen and drives it. The formaldehyde to attack the more hindered carbon as opposed to the less hindered carbon, because the borate here is forcing the formaldehyde to go here, and that's how you get that branch species.
So if that's deriving from C3 dihydroxyacid,
You can get from C3 dihydroxyacid, but you can also get from C3 glyceraldehyde. They will enolize to give you the same ene diol. Yeah.
okay. So
Okay.
Yeah, that sounds like a good lunchtime conversation.
All right.
I think we probably will end it there. We have a small token of appreciation for you to carry around the rest of the world.
Is this formally from the no?
No, that comes.
Oh, I thank you very much. Oh, even better.
So let's take this opportunity. Thanks, Steve. And, yeah, and so now there's lunch outside, and then the posters, where are they this afternoon?
Yeah, so the posting sessions at the MCIC. If you don't know where that is, there's plenty of students who can help show you where to go. The directions are also on the schedule printed out, so you grab one of those. Plus, presenters, please try to come 15 minutes early to get set up or so. Just you can walk in, just find a free board. It's not assigned or anything, and but you're good. Thanks.
So based on the question is, which is the best place to get the
well,
and